Quantum physics, at its core, is the branch of science that explores the fundamental building blocks of our universe. It concerns the behavior of matter and energy at the smallest scales, where the classical rules of physics give way to a realm of probabilities and uncertainties. Imagine a world where particles can exist in multiple places at once, where the mere act of observing something can alter its state, and where entangled particles communicate instantaneously across vast distances. This is the enchanting and often bewildering landscape that quantum physics unveils. To begin understanding quantum physics, it helps to contrast it with the classical physics that governs our everyday experiences. In the macroscopic world, objects follow predictable paths, and their behaviors can be precisely measured. A ball thrown in the air follows a clear trajectory, and the movement of planets around the Sun can be calculated with remarkable accuracy. This deterministic nature of classical physics provides a sense of order and predictability. However, when we shrink our view to the microscopic level, dealing with atoms and subatomic particles, a different set of rules emerges, one where certainty fades and probability takes center stage. At the heart of quantum physics lies the concept that particles, such as electrons and photons, exhibit both particle-like and wave-like properties. This duality means that these particles can behave as discrete units of matter or as waves that spread out and interfere with one another. This wave-particle duality challenges our traditional notions of what it means to be a particle or a wave, revealing a deeper, more complex nature of reality. One of the most intriguing aspects of quantum physics is the idea of superposition. Unlike classical objects that exist in one definite state at a time, quantum particles can exist in multiple states simultaneously. Imagine a coin spinning in the air, representing both heads and tails at the same time, until it lands and we observe the outcome. This superposition principle suggests that particles hold the potential for various outcomes, each with its own probability, until a measurement is made. Closely related to superposition is the concept of quantum entanglement. When particles become entangled, their states become intertwined in such a way that the state of one instantly influences the state of another, no matter how far apart they are. This phenomenon, which Einstein famously referred to as spooky action at a distance, hints at a profound interconnectedness within the fabric of the universe, where space and time no longer act as strict boundaries. Measurement in quantum physics plays a unique and pivotal role. Unlike in classical physics, where measuring a system can be a passive act, in the quantum realm, the act of measurement fundamentally alters the system being observed. This is known as the observer effect. When we measure a quantum system, we force it to choose a particular state from its range of possibilities, collapsing the superposition into a definite outcome. This interplay between observation and reality suggests that the act of seeing is intrinsically linked to the nature of what is being observed. The uncertainty inherent in quantum physics is encapsulated by Heisenberg's uncertainty principle, which states that certain pairs of properties, like position and momentum, cannot both be precisely measured at the same time. The more accurately we know one property, the less precisely we can know the other. This principle introduces a fundamental limit to our knowledge, emphasizing that at the quantum level, nature itself is intrinsically uncertain. Quantum physics also extends its reach into the realms of energy and fields. Quantum field theory, for instance, describes how particles are excitations of their respective fields, permeating all of space and interacting with one another in complex ways. This framework not only unifies our understanding of different particles, but also bridges the gap between quantum mechanics and special relativity, paving the way for a more comprehensive view of the universe. The applications of quantum physics are both profound and far-reaching. From the development of semiconductors and lasers to the emerging fields of quantum computing and quantum cryptography, the principles of quantum mechanics are driving technological advancements that promise to transform our world. Quantum computers, leveraging the principles of superposition and entanglement, aim to solve problems that are currently intractable for classical computers, potentially revolutionizing fields such as medicine, cryptography, and materials science. Now that we've covered the foundations of quantum physics, let's compare it to classical mechanics to really understand the differences. Classical versus quantum mechanics. In the serene expanse of our everyday experiences, the world unfolds with a comforting regularity. Objects move with predictable grace, governed by the timeless laws of classical mechanics. Imagine a leaf drifting gently to the ground, its path determined by the gentle push of the wind and the steadfast pull of gravity. This realm of physics, rooted in the principles established by Newton, offers a sense of order and certainty. Yet, beneath this familiar surface lies a deeper, more intricate layer of reality, where the rules we hold dear begin to dissolve, revealing the enigmatic dance of quantum mechanics. Classical mechanics paints a picture of a universe where every action has an equal and opposite reaction, where the motion of planets, the fall of an apple, and the swing of a pendulum can all be precisely predicted and measured. It is a world where cause and effect intertwine seamlessly, creating a harmonious symphony of motion that aligns with our intuitive understanding. In this macroscopic landscape, objects possess definite positions and velocities, moving along clear, unambiguous paths. The behavior of these objects is deterministic, meaning that given complete information about a system, one can predict its future with absolute certainty. Yet in the microscopic realm, where atoms and subatomic particles reside, the familiar rules of classical mechanics begin to wane, giving way to the mysterious principles of quantum mechanics. Here, the universe operates on a scale where uncertainty and probability reign supreme. Unlike the predictable trajectories of celestial bodies, quantum particles exhibit behaviors that challenge our deepest intuitions. They do not adhere to single fixed paths, but instead exist in a state of endless possibilities, their properties defined by probabilities rather than certainties. One of the most striking differences between classical and quantum mechanics is the concept of determinism versus probability. In classical mechanics, if we know the initial conditions of a system with perfect accuracy, we can predict its future states with unwavering precision. This deterministic nature fosters a sense of control and predictability, allowing us to engineer machines, build structures, and navigate the physical world with confidence. However, in the quantum realm, the very act of measuring a particle introduces an element of uncertainty. The more precisely we attempt to measure one property, such as its position, the less precisely we can know another, like its momentum. Another profound difference lies in the nature of reality, as described by each framework. Classical mechanics portrays a universe of distinct, separate objects, each with its own independent existence. In contrast, quantum mechanics reveals a world where particles are deeply interconnected, their states entangled in ways that transcend spatial separation. Quantum entanglement suggests that particles can instantaneously influence one another, regardless of the distance that separates them. Moreover, the concept of superposition in quantum mechanics introduces a layer of complexity absent in classical physics. While classical objects exist in one state at a time, quantum particles can inhabit multiple states simultaneously, their existence defined by a blend of possibilities until an observation is made. This delicate balance between potential and actuality creates a fluid reality where the act of measurement plays a pivotal role in shaping the outcome. It is a stark departure from the fixed, unchanging states of classical objects. The transition from classical to quantum mechanics also marks a shift in how we understand energy and forces. In the classical view, energy is a continuous quantity, flowing smoothly and predictably through systems. Quantum mechanics, however, introduces the idea of quantized energy levels, where particles can only occupy specific energy states. This discretization of energy unveils a world where transitions occur in leaps rather than gradual shifts, adding a layer of structure and complexity to our understanding of the fundamental forces that govern the universe. Furthermore, classical mechanics operates within a framework where time and space are absolute, serving as the unchanging backdrop against which events unfold. Quantum mechanics, influenced by the theories of relativity, begins to blur these distinctions, suggesting that time and space themselves may be dynamic and intertwined with the very fabric of reality. This interplay hints at a universe where the boundaries between past, present, and future are not as rigid as once thought, opening avenues for deeper exploration into the nature of existence. Despite these differences, classical and quantum mechanics are not isolated realms, but complementary facets of a unified physical theory. Classical mechanics serves as an excellent approximation for macroscopic phenomena, where the collective behavior of countless particles averages out the quantum uncertainties, restoring the predictability and order we observe in our daily lives. It is in this seamless integration that the true beauty of physics emerges, revealing a universe where the deterministic and the probabilistic coexist in a delicate balance, each illuminating different aspects of the same underlying reality. Classical mechanics offers a foundation of understanding, a familiar landscape where the rules are clear and the outcomes certain. Quantum mechanics, on the other hand, deals with a realm of mystery and wonder, where the very fabric of reality is woven from threads of probability and interconnectedness. The differences between classical and quantum mechanics are truly fascinating. But how did quantum mechanics even come to be? Let's explore the birth of this revolutionary field next. The birth of quantum mechanics. The early 20th century marked a pivotal moment in the history of science with the emergence of quantum mechanics. This new branch of physics revolutionized our understanding of the microscopic world, challenging the long-held principles of classical mechanics. Three key figures, Max Planck, Albert Einstein, and Niels Bohr, played instrumental roles in shaping the foundations of quantum theory. Max Planck is often credited with initiating the quantum revolution. In 1900, he was studying blackbody radiation, which is the emission of light from objects heated to high temperatures. Classical physics could not explain the observed spectrum of this radiation. To resolve this, Planck proposed that energy is not continuous, but comes in discrete units called quanta. He introduced Planck's constant, a fundamental value that describes the size of these energy packets. This idea was groundbreaking because it suggested that energy exchanges at the atomic level occur in fixed amounts, laying the groundwork for quantum theory. Building on Planck's work, Albert Einstein made significant contributions by exploring the nature of light. In 1905, Einstein explained the photoelectric effect, where light shining on certain materials ejects electrons from their surfaces. Classical wave theories of light could not account for the observed results. Einstein proposed that light consists of particles, or photons, each carrying a specific amount of energy. This particle theory of light not only explained the photoelectric effect, but also reinforced the concept of energy quantization. Einstein's work provided crucial evidence that supported the emerging quantum framework and earned him the Nobel Prize in Physics in 1921. Niels Bohr further advanced quantum mechanics with his model of the atom. In 1913, Bohr introduced a theory that combined classical mechanics with quantum ideas to explain the structure of the hydrogen atom. According to Bohr, electrons orbit the nucleus in specific quantized energy levels. Electrons can move between these levels by absorbing or emitting precise amounts of energy. corresponding to the difference between the energy levels. This model successfully explained the spectral lines of hydrogen and demonstrated how quantum principles could be applied to atomic structure. Bohr's work bridged the gap between classical and quantum physics, providing a more comprehensive understanding of atomic behavior. The collaboration and sometimes contentious interactions between these scientists fostered an environment of intense intellectual development. Bohr, for example, engaged in numerous discussions and debates with other physicists like Werner Heisenberg and Erwin Schrödinger, which further refined quantum theory. These interactions were crucial in addressing the paradoxes and challenges that quantum mechanics presented. Pushing the boundaries of what was known and understood, the birth of quantum mechanics was not an isolated event, but a gradual process of questioning and redefining existing theories. Planck, Einstein, and Bohr each addressed different aspects of physical phenomena, contributing unique insights that collectively formed the core of quantum theory. Their work demonstrated that classical physics, while effective for explaining macroscopic phenomena, was insufficient for understanding the complexities of the atomic and subatomic worlds. This period also highlighted the shift from deterministic to probabilistic interpretations of nature. Classical mechanics provided precise predictions based on initial conditions, but quantum mechanics introduced inherent uncertainties and probabilities. This fundamental change in perspective required scientists and thinkers to rethink the very nature of reality and measurement. The advancements made by these pioneers paved the way for future developments in quantum mechanics, including the formulation of quantum field theory and the exploration of quantum entanglement. Their legacy is evident in the technological innovations that rely on quantum principles, such as semiconductors, lasers, and modern electronics. Moreover, the philosophical implications of quantum mechanics continue to inspire debates about the nature of consciousness, reality, and the limits of human knowledge. In summary, the birth of quantum mechanics was a transformative period driven by the contributions of Max Planck, Albert Einstein, and Niels Bohr. Their groundbreaking ideas challenged classical notions and established a new framework for understanding the microscopic universe. The emergence of quantum mechanics was a true game-changer. Now let's delve into one of its most mind-bending concepts: wave-particle duality. The wave-particle duality stands as one of the most intriguing and fundamental concepts in quantum physics, reshaping our understanding of light and matter. At its core, this principle reveals that particles traditionally thought of as distinct entities like electrons and photons exhibit both particle-like and wave-like properties depending on how they are observed. This dual nature challenges our classical intuition, revealing a more nuanced and interconnected view of the microscopic world. Imagine light as a gentle stream flowing smoothly over rocks in a river. From a distance, the stream appears as a continuous flow, much like how light behaves as a wave, spreading out and creating patterns of interference and diffraction. These wave-like characteristics of light are evident in phenomena such as the colorful patterns seen when light passes through a prism, or the way waves on a pond create intricate ripples. This wave perspective allows us to understand how light can bend around obstacles and interfere with itself, creating regions of constructive and destructive interference. However, when we zoom in to examine light more closely, its behavior changes dramatically. Experiments like the photoelectric effect reveal that light can also behave as discrete packets of energy, called photons. In this particle view, light consists of individual particles that carry specific amounts of energy, much like individual droplets of water in a spray. This particle nature of light explains how it can knock electrons off a metal surface, a phenomenon that wave theory alone could not account for. Each photon interacts with electrons in a quantized manner, transferring energy in precise amounts rather than a continuous flow. The dual nature of light is not limited to photons alone. Electrons, which we typically consider as particles, also exhibit wave-like properties under certain conditions. When electrons pass through a double-slit apparatus, they create an interference pattern on a screen behind the slits, similar to waves overlapping and creating areas of reinforcement and cancellation. This wave behavior of electrons demonstrates that matter, too, possesses a dual character, bridging the gap between classical particles and waves. This duality is not just a curious anomaly, but a fundamental aspect of the quantum world. It suggests that the classical distinctions we draw between particles and waves are insufficient to fully describe the behavior of microscopic entities. Instead, quantum objects exist in a state that encompasses both aspects, revealing a deeper layer of reality that transcends our everyday experiences. One way to visualize wave-particle duality is to consider a coin spinning on a table. While spinning, the coin appears to blur between heads and tails, existing in a state of uncertainty until it lands. Similarly, quantum particles exist in a superposition of states, embodying both wave-like and particle-like properties until measured. This superposition allows particles to exhibit behaviors characteristic of both waves and particles, depending on the experimental setup and the nature of observation. The implications of wave-particle duality extend beyond theoretical curiosity, influencing various technological advancements. For instance, the development of lasers relies on the coherent wave properties of light, enabling precise control over its phase and direction. On the other hand, the understanding of photons as particles is crucial for technologies like photovoltaic cells, which convert light into electrical energy by harnessing the energy of individual photons. Wave-particle duality also plays a significant role in the field of quantum computing. Quantum bits, or qubits, leverage the dual nature of particles to exist in multiple states simultaneously, allowing for parallel processing and exponentially greater computational power compared to classical bits. This duality is harnessed to perform complex calculations and solve problems that are currently intractable for traditional computers. Moreover, wave-particle duality bridges the gap between classical and quantum physics, providing a framework that unifies our understanding of the natural world. It challenges the deterministic view of classical mechanics, introducing an element of probability and uncertainty that is inherent to quantum systems. This shift in perspective has profound philosophical implications, prompting us to reconsider our notions of reality, causality, and the nature of existence itself. In exploring wave-particle duality, we encounter the delicate balance between observation and reality. The act of measuring a quantum system influences its behavior, collapsing the wave function and determining whether it exhibits wave-like or particle-like properties. This interplay underscores the intricate relationship between the observer and the observed, highlighting the fundamental role that consciousness and measurement play in shaping the quantum landscape. Wave-particle duality is a concept that truly boggles the mind. But there's another quantum phenomenon that's equally perplexing: the observer effect. This effect is a fascinating and fundamental concept in quantum mechanics, illustrating how the act of measurement can influence the very system being observed. Unlike in classical physics, where measurements can be made without altering the system, in the quantum realm, observation plays an active role in shaping reality. This principle challenges our traditional understanding of how the world operates, revealing a deeper connection between the observer and the observed. Imagine a serene lake, its surface calm and undisturbed. When a pebble is thrown into the water, ripples emerge, altering the lake's once still surface. Similarly, in quantum mechanics, particles exist in a state of potential, their properties undefined until they are measured. The act of observation, much like the pebble disrupting the lake, causes the system to settle into a definite state from a range of possibilities. At the heart of the observer effect is the concept of the wave function, a mathematical description that encapsulates all the possible states a quantum system can occupy. Before measurement, a particle such as an electron exists in a superposition, meaning it simultaneously holds multiple states or positions. This superposition is a delicate balance, a blend of probabilities that defines the likelihood of finding the particle in any given state. When a measurement is made, the wave function collapses and the particle assumes a specific state. This collapse is not merely a passive observation, but an active intervention that determines the outcome. The precise nature of this interaction has been a subject of intense debate and exploration, leading to various interpretations of quantum mechanics. One way to visualize the observer effect is through the famous double-slit experiment. In this setup, particles like electrons are fired at a barrier with two slits, and their impact is recorded on a screen behind the barrier. When not observed, electrons create an interference pattern on the screen, behaving like waves that pass through both slits simultaneously and interfere with each other. However, when a measurement device is placed to observe which slit an electron passes through, the interference pattern disappears, and the electrons behave like individual particles, passing through one slit or the other. This shift from wave-like to particle-like behavior upon measurement highlights the profound influence that observation has on quantum systems. It suggests that the act of measuring is not merely revealing a pre-existing state, but is actively involved in creating that state. This interplay between observer and system blurs the lines between the two, introducing a level of interaction that is absent in classical physics. The observer effect also underscores the inherent uncertainty and probabilistic nature of quantum mechanics. Werner Heisenberg's uncertainty principle complements this idea by stating that certain pairs of properties, such as position and momentum, cannot both be precisely measured simultaneously. The more accurately one property is known, the less precisely the other can be determined. This principle reinforces the notion that at the quantum level there are fundamental limits to what can be known, emphasizing that uncertainty is not just a matter of measurement precision, but a core feature of reality itself. Philosophically, the observer effect urges us to contemplate the nature of reality and our place within it. It challenges the notion of an objective, observer-independent universe, suggesting instead that reality is intertwined with the act of observation. This perspective has profound implications, not only for physics but also for our broader understanding of existence and consciousness. Various interpretations of quantum mechanics attempt to explain the observer effect, each offering different perspectives on the relationship between measurement and reality. The Copenhagen Interpretation, one of the earliest and most widely taught interpretations, posits that the wave function collapse is a fundamental aspect of measurement, with no deeper underlying mechanism. In contrast, the many worlds interpretation suggests that all possible outcomes of a measurement actually occur, each in its own separate branch of the universe, thereby avoiding the need for wave function collapse altogether. Another interpretation, known as quantum decoherence, provides a mechanism by which quantum systems interact with their environments, leading to the apparent collapse of the wave function without requiring a conscious observer. Decoherence explains how classical properties emerge from quantum systems through interactions that distribute information about the system's state into the environment, effectively measuring the system in a way that makes superpositions unobservable at macroscopic scales. Regardless of the interpretation, the observer effect remains a cornerstone of quantum mechanics, highlighting the intricate and often counterintuitive relationship between measurement and reality. It serves as a reminder that our understanding of the universe is deeply connected to the ways in which we interact with it, revealing a level of complexity and interdependence that continues to inspire scientific inquiry and philosophical reflection. In practical terms, the observer effect has significant implications for the development of quantum technologies. In quantum computing, for example, the delicate superpositions and entangled states that provide the potential for immense computational power are highly sensitive to external measurements and interactions. Controlling and mitigating the observer effect is crucial for maintaining the coherence of quantum states, enabling the realization of powerful and reliable quantum devices. Similarly, in quantum cryptography, the observer effect is harnessed to ensure secure communication. Quantum key distribution protocols rely on the principle that any attempt to eavesdrop on a quantum system will disturb its state, thereby revealing the presence of an intruder. This property provides a level of security that is fundamentally unattainable with classical communication methods, showcasing the practical utility of understanding and managing the observer effect. The observer effect is a prime example of how quantum mechanics challenges our classical intuitions. Speaking of challenges, let's dive into another quantum principle that defies our everyday expectations: the Heisenberg's uncertainty principle. This principle stands as a fundamental pillar in the realm of quantum mechanics, redefining our understanding of measurement and precision at the smallest scales of the universe. This principle articulates a profound limitation. It is impossible to simultaneously know both the exact position and the exact momentum of a particle with absolute certainty. This inherent limitation challenges the very notion of determinism that classical physics upholds, introducing a layer of inherent unpredictability into the fabric of reality. To visualize the uncertainty principle, imagine trying to capture the precise location and speed of a hummingbird in flight. The more accurately you attempt to pinpoint its position with a camera, the more you might disturb its motion, making its speed harder to determine. Similarly, in the quantum world, measuring a particle's position with greater accuracy inevitably introduces greater uncertainty in its momentum, and vice versa. This interplay between position and momentum is not due to flaws in our measurement tools, but is a fundamental property of nature itself. At the heart of the uncertainty principle lies the wave-particle duality of quantum objects. Particles such as electrons exhibit both wave-like and particle-like behaviors. When we attempt to measure the position of a particle precisely, we engage with its particle aspect, causing its wave function, a mathematical description of its quantum state, to collapse. This collapse narrows down the possible positions, but broadens the range of possible momenta. Conversely, measuring momentum precisely spreads out the possible positions of the particle. This delicate balance ensures that certain pairs of physical properties remain intrinsically uncertain. The mathematical formulation of the uncertainty principle reveals that the product of the uncertainties in position and momentum is always greater than or equal to a specific constant, known as Planck's constant divided by 4 pi. This relationship underscores that the uncertainties are not arbitrary, but are bound by the fundamental constants of nature. It signifies that at a quantum level, the universe does not allow for complete precision, embodying a natural limit to our knowledge. This principle has far-reaching implications beyond theoretical physics. It influences our understanding of the microscopic world, where particles behave in ways that defy classical intuition. The uncertainty principle suggests that the universe at its core is governed by probabilities rather than certainties, weaving a complex web of possibilities that define the behavior of matter and energy. In practical terms, the uncertainty principle plays a crucial role in the stability of atoms. Without this inherent uncertainty, electrons would spiral into the nucleus, causing atoms to collapse. Instead, the principle ensures that electrons occupy regions around the nucleus with probabilities that prevent such collapse, maintaining the integrity of matter as we know it. This delicate balance is essential for the formation of chemical bonds and the existence of the diverse materials that make up our world. Moreover, the uncertainty principle has implications for the development of quantum technologies. In quantum computing, for instance, the ability to manipulate qubits relies on understanding and managing the uncertainties inherent in their states. Precision in quantum measurements is both a challenge and a necessity, as it dictates the reliability and efficiency of quantum operations. Similarly, in quantum cryptography, the uncertainty principle underpins the security of communication protocols, ensuring that any attempt to intercept information introduces detectable disturbances. Philosophically, Heisenberg's uncertainty principle invites us to reconsider our perceptions of reality and knowledge. It suggests that there are fundamental limits to what can be known, reshaping our understanding of observation and existence. This principle bridges the gap between the observer and the observed, highlighting a universe where certainty is replaced by a dance of probabilities and potentialities. Different interpretations of quantum mechanics offer varied perspectives on the uncertainty principle. The Copenhagen Interpretation views the uncertainty as a reflection of our incomplete knowledge about a system, emphasizing the role of measurement in defining reality. In contrast, the many worlds interpretation posits that all possible outcomes of a quantum measurement actually occur, each in its own distinct branch of the universe, thereby circumventing the need for uncertainty in a single reality. Experimental evidence continues to support the uncertainty principle, reinforcing its status as a cornerstone of quantum theory. Techniques such as electron microscopy and atomic spectroscopy operate within the constraints imposed by this principle, pushing the boundaries of what can be measured and understood. These advancements not only validate the uncertainty principle, but also expand our capacity to explore and manipulate the quantum world. In essence, Heisenberg's uncertainty principle reveals a universe where precision is inherently limited, where the act of measurement influences the very properties it seeks to determine. The uncertainty principle is a true game changer in our understanding of the quantum world. But there's another quantum phenomenon that's equally mind-bending: entanglement. So what is quantum entanglement? It's often referred to as spooky action at a distance, a term coined by Albert Einstein. Entanglement challenges our classical understanding of how objects interact and influence one another across space and time. This concept reveals a level of interconnectedness between particles that defies conventional intuition, opening doors to profound implications in both science and technology. At its core, quantum entanglement occurs when two or more particles become linked in such a way that the state of one instantly influences the state of the other, regardless of the distance separating them. Imagine two dancers performing a synchronized routine. No matter how far apart they are, their movements remain perfectly in sync, each dancer responding instantaneously to the other's motions. In the quantum world, entangled particles exhibit a similar kind of synchronization, but on a scale that transcends our everyday experiences. To understand entanglement, consider the example of a pair of electrons. When these electrons become entangled, their properties become interconnected. If one electron is measured to have a specific spin in one direction, the other electron's spin in the opposite direction is immediately determined, even if the electrons are light years apart. This immediate correlation occurs without any known signal traveling between the particles, suggesting a connection that operates beyond the limitations of space and time, as we understand them. The phenomenon of entanglement was first highlighted in the early 20th century through the work of physicists like Einstein, Boris Podolsky, and Nathan Rosen in their famous EPR paradox. They proposed a thought experiment to illustrate what they saw as a flaw in quantum mechanics, questioning how two particles could remain connected in such a way. However, subsequent experiments have consistently confirmed the existence of entanglement, reinforcing its validity and challenging our classical notions of locality and causality. One of the key experiments demonstrating entanglement is the Bell test, which tests the predictions of quantum mechanics against those of classical physics. These experiments involve measuring the properties of entangled particles in various configurations and have consistently supported the quantum mechanical predictions, showing that entangled particles exhibit correlations that cannot be explained by any local hidden variable theory. This evidence firmly establishes entanglement as a fundamental aspect of quantum reality. Entanglement has significant implications for our understanding of the universe. It suggests that the quantum world is deeply interconnected, where the state of one particle cannot be fully described without considering its entangled partner. This interconnectedness hints at a level of unity within the fabric of reality, where the boundaries between individual particles blur, revealing a more holistic view of the cosmos. Beyond its theoretical implications, quantum entanglement holds promise for practical applications that could revolutionize technology. One of the most exciting areas is quantum computing. Quantum computers leverage entanglement to perform complex calculations at speeds unattainable by classical computers. By entangling qubits, the fundamental units of quantum information, these machines can process vast amounts of data simultaneously, solving problems that were previously thought to be intractable. Another promising application is quantum cryptography, which utilizes entanglement to create unbreakable encryption methods. Quantum key distribution protocols rely on the properties of entangled particles to ensure secure communication. Any attempt to intercept or measure the entangled particles disrupts their state, instantly revealing the presence of an eavesdropper. This inherent security feature makes quantum cryptography a powerful tool for protecting sensitive information in an increasingly digital world. Entanglement also plays a crucial role in the emerging field of quantum teleportation, a process by which the quantum state of a particle is transferred from one location to another without moving the particle itself. By using entangled particles, scientists can transmit information instantaneously across vast distances, paving the way for advancements in communication and information transfer that were once considered purely theoretical. Despite these advancements, entanglement continues to challenge our understanding of reality. It raises fundamental questions about the nature of space, time, and information. How can two particles influence each other instantaneously across the universe? Does entanglement imply a hidden layer of reality where everything is interconnected? These questions remain at the forefront of scientific inquiry, driving researchers to explore the depths of quantum mechanics and the mysteries it holds. In practical terms, harnessing entanglement requires overcoming significant challenges. Maintaining entangled states over long distances and ensuring their stability in the face of environmental disturbances are ongoing areas of research. Innovations in quantum error correction, materials science, and experimental techniques are essential for advancing our ability to control and utilize entanglement effectively. As we continue to explore the depths of quantum entanglement, we uncover layers of reality that were previously hidden from our view. Each discovery not only enhances our technological capabilities, but also deepens our appreciation for the intricate and often counterintuitive nature of the quantum world. Entanglement serves as a bridge between the abstract principles of quantum mechanics and tangible applications that have the potential to transform our lives. Quantum entanglement is a truly mind-bending phenomenon, but there's another quantum effect that seems to defy common sense. Tunneling. Quantum tunneling. This is a remarkable phenomenon in the realm of quantum mechanics, where particles possess the ability to traverse barriers that, according to classical physics, should be insurmountable. This concept challenges our conventional understanding of motion and energy, revealing the intricate and often surprising behaviors that govern the microscopic world. Imagine a ball rolling towards a hill. In classical physics, if the ball doesn't have enough energy to reach the top of the hill, it will simply roll back down. The hill acts as a barrier, preventing the ball from passing through without sufficient force. However, in the quantum universe, particles like electrons can exhibit behaviors that defy this straightforward logic. Even when they seemingly lack the necessary energy to overcome a barrier, they can still appear on the other side, as if they have tunneled through the obstacle. This intriguing capability arises from the wave-like nature of particles in quantum mechanics. Unlike macroscopic objects which follow well-defined paths, quantum particles exist as wave functions, probabilistic descriptions of their possible positions and states. These wave functions can extend beyond physical barriers, allowing particles to have a finite probability of being found on the opposite side, despite not having enough energy to surmount the barrier in a classical sense. A classic illustration of quantum tunneling is found in the behavior of electrons within atoms. Electrons orbit the nucleus in regions called orbitals, which are defined by specific energy levels. According to classical physics, an electron would need a certain amount of energy to move from one orbital to another, or to escape the atom entirely. Yet, quantum tunneling allows electrons to transition between orbitals, or even leave the atom without acquiring the requisite energy. This process is essential for various phenomena, including radioactive decay and the functioning of certain types of electronic devices. One of the most practical applications of quantum tunneling is found in tunnel diodes, a type of semiconductor device. Tunnel diodes exploit the tunneling effect to achieve very high-speed operation and negative resistance, making them valuable components in high-frequency electronics and oscillators. Without quantum tunneling, the development of such advanced electronic technologies would be significantly hindered. Quantum tunneling also plays a crucial role in nuclear fusion, the process that powers stars, including our Sun. In the extreme conditions of a star's core, hydrogen nuclei must overcome their mutual electrostatic repulsion to fuse into helium. Classical physics suggests that the temperatures and pressures required for this fusion are extraordinarily high. However, quantum tunneling allows these nuclei to occasionally pass through the energy barrier, enabling fusion to occur even at lower energies than would otherwise be necessary. This delicate balance sustains the life of stars, and by extension, the existence of galaxies and the broader cosmos. The phenomenon of quantum tunneling also contributes to the understanding of chemical reactions. In certain reactions, atoms or molecules must overcome energy barriers to rearrange into new configurations. Quantum tunneling provides a pathway for these transformations, allowing reactions to proceed at rates that classical theories would predict to be much slower. This insight enhances our comprehension of chemistry at a fundamental level, influencing fields ranging from material science to biology. Despite its profound implications, quantum tunneling remains a subject of deep scientific inquiry and fascination. The very idea that particles can defy seemingly impenetrable barriers prompts us to rethink the boundaries of possibility within the quantum realm. It underscores the inherent uncertainties and probabilistic nature of quantum mechanics, where outcomes are not strictly determined but instead governed by probabilities and wave-like behaviors. The mathematical foundation of quantum tunneling is rooted in the Schrödinger equation, which describes how the wave function of a quantum system evolves over time. Solutions to this equation reveal that wave functions can penetrate barriers to a certain extent, allowing particles to emerge on the other side, with a probability that depends on factors like the barrier's height and width, as well as the particle's energy. This probabilistic nature means that while tunneling is not guaranteed, it becomes increasingly likely under specific conditions, such as thinner or lower barriers and higher particle energies. Experimental evidence for quantum tunneling is abundant and diverse, spanning various scales and systems, from the tunneling of electrons in solid-state devices to the escape of alpha particles from atomic nuclei. The observable effects of tunneling provide compelling support for its existence. These experiments not only validate the theoretical predictions, but also inspire new technologies and applications that harness the unique properties of tunneling. Philosophically, quantum tunneling invites contemplation about the nature of reality and the limits of human perception. It blurs the lines between what is possible and impossible, revealing a universe where the rules are governed by probabilities and wave functions rather than deterministic paths. This perspective encourages a more nuanced understanding of existence, where the boundaries of physical barriers are not absolute, but permeable. Under the right quantum conditions, quantum tunneling continues to inspire innovation and discovery. Advances in quantum computing, for instance, may leverage tunneling effects to enhance computational processes and solve complex problems more efficiently than classical systems. Similarly, advancements in nanotechnology and materials science benefit from a deeper understanding of tunneling, enabling the design of devices with unprecedented precision and functionality. As we explore the depths of quantum tunneling, we uncover layers of complexity that enrich our appreciation for the quantum world. This phenomenon exemplifies the delicate interplay between energy, probability, and wave-like behavior, highlighting the extraordinary capabilities that arise from the fundamental principles of quantum mechanics. Quantum tunneling not only expands our scientific horizons but also deepens our appreciation for the intricate and often surprising nature of the universe. Quantum tunneling stands as a testament to the remarkable and often counterintuitive behaviors that define the quantum realm. By allowing particles to traverse barriers that seem insurmountable, tunneling challenges our classical intuitions and opens up a world of possibilities in both scientific understanding and technological advancement. It serves as a bridge between the abstract principles of quantum theory and tangible applications that shape our modern world, illustrating the profound impact that quantum mechanics has on our perception of reality and the potential it holds for future innovations. Quantum tunneling is a prime example of how quantum mechanics defies our everyday intuitions. But there's another key aspect of quantum mechanics that sets it apart from classical physics: the role of probability. Let's explore the role of probability in quantum mechanics. At the heart of quantum mechanics lies the concept that particles, such as electrons and photons, do not have definite positions or velocities until they are observed. Instead, their properties are described by a wave function, a mathematical tool that encapsulates all the possible states a particle can occupy. This wave function evolves smoothly over time, governed by the Schrödinger equation, predicting the probabilities of finding a particle in various states rather than providing exact values. Unlike classical mechanics, where the future behavior of an object can be predicted with precision given its current state, quantum mechanics embraces uncertainty. This shift from determinism to probabilistic descriptions marks a fundamental change in how we understand the universe. In the classical world, if you know the position and velocity of a ball, you can predict its future trajectory. In the quantum realm, knowing the wave function allows you to calculate the likelihood of different outcomes, but not to pinpoint a single, definite result. One of the most illustrative experiments demonstrating the role of probability is the double-slit experiment. When particles like electrons are fired at a barrier with two slits, and no measurement is made to determine which slit each electron passes through, an interference pattern emerges on a detection screen behind the barrier. This pattern suggests that each electron behaves like a wave, passing through both slits simultaneously and interfering with itself. However, if a measurement is made to observe which slit an electron goes through, the interference pattern disappears, and the electrons behave like individual particles, passing through one slit or the other. The act of measurement changes the outcome, highlighting the intrinsic probabilistic nature of quantum mechanics. Probability in quantum mechanics is not just a tool for prediction. It reflects a deeper aspect of reality. The probabilities arise from the fundamental nature of particles at the quantum level, where properties are not fixed but exist in a range of possibilities. This probabilistic framework challenges our classical intuitions, suggesting that the universe is inherently uncertain at its core. The probabilistic interpretation is formalized through the Born rule, which connects the wave function to measurable probabilities. According to the Born rule, the square of the amplitude of the wave function at a particular point gives the probability density of finding the particle there. This relationship transforms the abstract wave function into tangible predictions about the likelihood of various outcomes, bridging the gap between mathematical theory and experimental observation. Probability also plays a crucial role in understanding quantum entanglement, where particles become interconnected in such a way that the state of one instantly influences the state of another, regardless of the distance between them. In entangled systems, the probabilities of the particle's properties are interdependent, meaning that measuring one particle affects the probabilities associated with the other. This interconnectedness underscores the non-local nature of quantum mechanics, where probability transcends traditional spatial boundaries. In addition to foundational experiments, probability in quantum mechanics has practical applications that drive technological advancements. Quantum computing, for instance, leverages the probabilistic states of qubits to perform complex calculations. Unlike classical bits, which are either 0 or 1, qubits can exist in superpositions of both states simultaneously, allowing quantum computers to process vast amounts of information in parallel. The probabilistic nature of qubits is harnessed to explore multiple solutions at once, potentially solving problems that are currently beyond the reach of classical computers. Quantum cryptography also relies on probability to ensure secure communication. Quantum key distribution protocols use the probabilistic behavior of particles to detect any attempts at eavesdropping. If an unauthorized party tries to intercept the quantum signals, the probabilities of the particle's states are altered, revealing the presence of the intrusion. This probabilistic security feature makes quantum cryptography a powerful tool for protecting sensitive information. Despite its successes, the probabilistic nature of quantum mechanics raises profound philosophical questions about the nature of reality and our ability to comprehend it. Some interpretations suggest that probability is a fundamental aspect of the universe, while others propose that underlying deterministic processes might exist, but are hidden from our current understanding. These debates highlight the ongoing exploration and refinement of quantum theory, as scientists and philosophers seek to unravel the mysteries of probability in the quantum realm. Experimental advancements continue to push the boundaries of our probabilistic understanding. Techniques such as quantum tomography allow for detailed reconstruction of wave functions, providing deeper insights into the probabilistic behaviors of quantum systems. These experiments not only validate the probabilistic framework, but also inspire new technologies that harness the unique properties of quantum mechanics. In summary, probability is not merely an abstract concept in quantum mechanics. It is a fundamental aspect that shapes our understanding of the microscopic world. By embracing uncertainty and exploring the range of possible outcomes, quantum mechanics offers a richer, more nuanced view of reality. This probabilistic foundation challenges classical notions of determinism, revealing a universe where possibilities abound and the act of observation plays a pivotal role in defining existence. The probabilistic nature of quantum mechanics is a key concept that sets it apart from classical physics. But how do we interpret these probabilities? One of the most widely accepted interpretations is the Copenhagen Interpretation. The concept of the Copenhagen Interpretation forms the cornerstone of our standard understanding of quantum mechanics. developed in the 1920s primarily by Niels Bohr and Werner Heisenberg. This interpretation provides a framework for making sense of the peculiar behaviors observed at the quantum level. It has become the prevailing view among physicists, offering insights into the nature of reality, measurement, and the role of the observer in the quantum realm. At its core, the Copenhagen interpretation posits that quantum systems exist in a state of superposition, where particles can occupy multiple states simultaneously. These superpositions are described by a wave function, a mathematical construct that encapsulates all possible outcomes of a quantum event. However, unlike classical systems where properties like position and momentum can be precisely determined, quantum systems only yield probabilities for various outcomes when measured. One of the fundamental aspects of this interpretation is the concept of wave function collapse. Before a measurement is made, a particle's wave function represents a range of possible states, each with a certain probability. When an observation occurs, the wave function collapses to a single state, and the particle assumes definite properties. This transition from a probabilistic wave function to a specific outcome challenges our classical intuition, where objects possess definite properties regardless of observation. The Copenhagen interpretation also emphasizes the inherent uncertainty in quantum mechanics, aligning with Heisenberg's uncertainty principle. This principle asserts that certain pairs of properties, such as position and momentum, cannot both be precisely measured simultaneously. The more accurately one property is known, the less precisely the other can be determined. This inherent limitation is not due to flaws in measurement tools, but is a fundamental feature of nature as described by quantum theory. A key element of the Copenhagen interpretation is the duality of wave and particle nature. Particles like electrons and photons exhibit both wave-like and particle-like properties, depending on the experimental setup. For instance, in the double-slit experiment, particles create an interference pattern characteristic of waves when not observed. However, when measurements are made to determine which slit a particle passes through, the interference pattern disappears and particles behave as discrete entities. This dual behavior underscores the complex nature of quantum objects and the influence of observation on their properties. The role of the observer is another critical component of the Copenhagen interpretation. It suggests that the act of measurement is not merely a passive observation, but an active process that influences the state of the quantum system. This interplay raises profound questions about the nature of reality and the extent to which consciousness or observation shapes the physical world. While some interpretations extend this role to include the observer's consciousness, the Copenhagen interpretation primarily focuses on the interaction between the measuring apparatus and the quantum system. Despite its widespread acceptance, the Copenhagen interpretation is not without its critics and alternative viewpoints. One notable challenge comes from the many worlds interpretation, which proposes that all possible outcomes of a quantum measurement actually occur in separate branching universes. This view eliminates the need for wave function collapse by suggesting that every possibility is realized, but it introduces a complex multiverse concept that differs significantly from the Copenhagen framework. Another alternative is the de Broglie-Bohm pilot wave theory, which introduces hidden variables to maintain determinism in quantum mechanics. This theory posits that particles have definite positions and velocities guided by a pilot wave, preserving a classical sense of reality while accounting for quantum phenomena. Unlike the Copenhagen interpretation, which embraces probabilistic outcomes, the pilot wave theory seeks to restore determinism by adding underlying variables that are not directly observable. Despite these alternative interpretations, the Copenhagen interpretation remains the standard view due to its simplicity and effectiveness in explaining a wide range of quantum phenomena. It provides a practical approach for predicting experimental outcomes and has been instrumental in the development of quantum technologies such as semiconductors, lasers, and quantum computing. The interpretation's focus on probabilities and wave function collapse offers a coherent framework that aligns with empirical observations, making it a foundational pillar in the study of quantum mechanics. The Copenhagen interpretation also plays a significant role in shaping philosophical discussions about the nature of reality and knowledge. It challenges the classical notion of an objective reality independent of observation, suggesting instead that reality at the quantum level is intrinsically linked to the act of measurement. This perspective has influenced debates in philosophy of science, particularly concerning determinism, objectivity, and the limits of human knowledge. In practical applications, the Copenhagen interpretation informs the design and interpretation of experiments in quantum mechanics. It guides how scientists approach measurements, data analysis, and the formulation of new theories. By embracing the probabilistic nature of quantum systems, researchers can develop more accurate models and technologies that harness the unique properties of quantum particles. Furthermore, the interpretation has implications for emerging fields such as quantum information theory and quantum computing. Understanding the probabilistic behavior of quantum bits qubits and the role of entanglement in information processing relies heavily on the principles outlined by the Copenhagen framework. This foundation enables advancements in areas like secure communication, complex problem solving, and the development of new computational paradigms that surpass classical limitations. In summary, the Copenhagen interpretation provides a comprehensive and widely accepted framework for understanding quantum mechanics. It emphasizes the probabilistic nature of quantum systems, the role of wave function collapse, and the influence of measurement on physical states. While alternative interpretations offer different perspectives, the Copenhagen view remains integral to both theoretical and practical advancements in quantum physics. By accepting the inherent uncertainties and probabilistic outcomes of quantum mechanics, the Copenhagen interpretation continues to guide our exploration and application of the fascinating and complex behaviors that define the quantum world. The Copenhagen interpretation is a widely accepted framework for understanding quantum mechanics, but there's another intriguing interpretation that offers a radically different perspective: the many worlds interpretation. Let's explore this mind-bending concept next. Ever pondered what happens when a quantum event offers multiple outcomes? The many worlds interpretation provides a fascinating alternative perspective to understanding the intricate behaviors of particles at the quantum level. Proposed by physicist Hugh Everett in 1957, this interpretation challenges conventional notions of reality, suggesting that every possible outcome of a quantum event actually occurs, each in its own distinct universe. At the heart of the many worlds interpretation is the idea that the wave function, which describes the probabilities of a quantum system's various states, never collapses. Unlike the Copenhagen interpretation, where measurement causes the wave function to reduce to a single outcome, many worlds posits that all possible outcomes are realized, each in a separate, branching universe. This means that for every quantum event with multiple possible results, the universe splits into parallel branches, each representing a different outcome. To visualize this, imagine flipping a coin. In the classical view, the coin lands either heads or tails, and only one outcome is realized. However, according to many worlds, both outcomes occur, each in its own parallel universe. In one universe, the coin lands heads, while in another, it lands tails. This branching continues with every quantum event, creating an ever-expanding multitude of parallel universes where every conceivable outcome is actualized. This interpretation eliminates the randomness and probability inherent in quantum mechanics by asserting that all possibilities are equally real. Instead of probabilities reflecting our ignorance of the exact outcome, they represent the existence of multiple equally valid realities. Each branch of the universe operates independently, with no interaction between them once the split occurs. This seamless integration of determinism and reality offers a coherent framework that aligns with the mathematical formalism of quantum mechanics without introducing wave function collapse. One of the most compelling aspects of the many worlds interpretation is its ability to resolve certain paradoxes in quantum mechanics. For instance, Schrödinger's cat, a thought experiment where a cat in a box is simultaneously alive and dead until observed, finds a natural explanation in many worlds. Instead of the cat being in a superposition of states, the universe splits into two branches, one where the cat is alive and another where it is dead. This approach removes the need for a mysterious collapse of the wave function, providing a straightforward account of the observed reality. Despite its elegant resolution of quantum paradoxes, the many worlds interpretation is not without its challenges and controversies. One significant criticism is the sheer number of parallel universes it implies. The idea of an ever-branching multiverse raises questions about the nature of these universes and the mechanisms behind their creation. Additionally, the interpretation faces scrutiny regarding its testability. Since the parallel branches do not interact, it becomes difficult to devise experiments that can confirm the existence of these alternate realities, leaving the many worlds interpretation largely in the realm of philosophical debate. Nevertheless, many worlds has garnered substantial support within the physics community due to its consistency with the deterministic nature of the Schrödinger equation. By avoiding the need for wave function collapse, it maintains the continuity and unitarity of quantum evolution, preserving the mathematical integrity of quantum theory. This alignment with the formalism of quantum mechanics makes many worlds a compelling alternative to interpretations that introduce additional postulates or mechanisms. The implications of the many worlds interpretation extend beyond theoretical physics, influencing fields such as cosmology, information theory, and even philosophy. In cosmology, the concept of a multiverse aligns with theories that suggest our universe is just one of many within a larger cosmic landscape. In information theory, the interpretation offers a unique perspective on quantum computing, where computations can be viewed as occurring simultaneously across multiple branches of the universe, enhancing the potential for parallel processing and problem-solving. Philosophically, many worlds invites us to reconsider our understanding of existence, reality, and identity. If every possible outcome of every event spawns a new universe, the notion of individuality and uniqueness becomes more complex. It raises profound questions about the nature of consciousness and the self. If there are countless versions of ourselves experiencing every possible outcome, what does that mean for our sense of identity and continuity? In practical terms, while many worlds does not currently offer distinct technological applications separate from other interpretations, its influence permeates the foundational understanding of quantum mechanics. As quantum technologies advance, particularly in areas like quantum computing and quantum cryptography, the underlying interpretations of quantum mechanics will continue to shape how we develop and utilize these innovations. Understanding the many worlds framework provides a deeper appreciation for the complexities and possibilities inherent in quantum systems, fostering a more comprehensive approach to scientific inquiry and technological development. In conclusion, the many worlds interpretation presents a bold and expansive view of reality, where every possible outcome of a quantum event is realized in its own universe. by maintaining the deterministic evolution of the wave function and eliminating the need for wave function collapse. It offers a coherent and elegant framework that aligns with the mathematical foundations of quantum mechanics. While it raises intriguing philosophical questions and faces challenges regarding its empirical verification, many worlds remains a significant and influential perspective. The many worlds interpretation offers a mind-bending alternative to the Copenhagen interpretation, but there's yet another approach that seeks to reconcile quantum mechanics with determinism: the pilot wave theory. Should we reconsider the conventional understanding of quantum mechanics, exploring alternative theories that offer different perspectives on the behavior of particles? The pilot wave theory, also known as the de Broglie-Bohm theory, presents such an alternative by introducing the concept of hidden variables to explain quantum phenomena. This theory seeks to provide a deterministic framework within the inherently probabilistic world of quantum mechanics, addressing some of the ambiguities and paradoxes that arise from traditional interpretations. At the foundation of the pilot wave theory lies the idea that particles possess definite positions and velocities at all times, guided by a deterministic pilot wave. Unlike the Copenhagen interpretation, which relies on wave function collapse and inherent uncertainties, the pilot wave theory maintains that particles follow precise trajectories influenced by an underlying wave. This approach reintroduces a level of determinism to quantum mechanics, suggesting that the apparent randomness observed in experiments is a result of our limited knowledge of these hidden variables. To visualize this, imagine a boat navigating through water. The boat's path is determined by the currents and waves acting upon it, providing a clear and predictable route. Similarly, in the pilot wave theory, the pilot wave acts as a guiding force that directs the particle's motion. The wave carries information about the environment and potential interactions, ensuring that the particle moves in a consistent and deterministic manner despite the complexities of its surroundings. One of the key advantages of the pilot wave theory is its ability to reproduce all the successful predictions of standard quantum mechanics while offering a clearer ontological picture. By positing that particles have well-defined properties independent of observation, the theory resolves some of the philosophical dilemmas associated with the role of the observer in quantum mechanics. This eliminates the need for wave function collapse, presenting a more intuitive understanding of quantum processes where the behavior of particles is governed by deterministic laws. The pilot wave theory also provides elegant solutions to quantum paradoxes such as Schrödinger's cat and the measurement problem. In this framework, the cat in Schrödinger's thought experiment is either alive or dead, determined by the hidden variables guiding the particles within the system. There is no superposition of states. Instead, the outcome is predetermined by the underlying pilot wave. This deterministic approach aligns more closely with classical intuitions, bridging the gap between classical and quantum physics by reintroducing definitive states for particles. Despite its strengths, the pilot wave theory faces challenges and criticisms. One significant hurdle is its compatibility with relativistic quantum mechanics and quantum field theory. Extending the theory to accommodate the principles of relativity without introducing inconsistencies remains an area of active research. Additionally, the existence of hidden variables has yet to be empirically confirmed, and the theory must account for the vast number of variables that would be required to describe complex quantum systems fully. Another point of contention is the theory's non-locality, meaning that the pilot wave can instantaneously influence particles regardless of the distance separating them. This feature aligns with the phenomenon of quantum entanglement, but raises questions about causality and the nature of information transfer in the universe. While non-locality is a recognized aspect of quantum mechanics, integrating it seamlessly within a deterministic framework presents conceptual and practical challenges. Despite these challenges, the pilot wave theory continues to inspire research and debate within the physics community. Its deterministic nature offers a compelling alternative to the probabilistic interpretations of quantum mechanics, appealing to those who seek a more intuitive and less abstract understanding of quantum phenomena. Ongoing advancements in experimental techniques and theoretical developments may provide further insights into the viability of hidden variable theories and their role in the broader landscape of quantum physics. In practical applications, the principles of the pilot wave theory have influenced areas such as quantum hydrodynamics, where researchers study fluid-like behaviors in quantum systems. These studies offer tangible demonstrations of wave-particle interactions and provide valuable data that can inform and refine theoretical models. By bridging the gap between classical fluid dynamics and quantum behavior, the pilot wave theory fosters a more integrated approach to understanding the complexities of the quantum world. As researchers continue to investigate the potential of hidden variable theories, the pilot wave theory stands as a testament to the diversity of thought and the relentless pursuit of understanding that drives scientific progress. By exploring alternative interpretations like the pilot wave theory, we expand the horizons of quantum mechanics, uncovering new layers of complexity and paving the way for future discoveries that may one day bridge the gap between determinism and the probabilistic nature of the quantum realm. The pilot wave theory offers an intriguing alternative to the Copenhagen and many worlds interpretations. But there's another concept that helps explain how the quantum world transitions to the classical realm: quantum decoherence. What prevents us from witnessing the strange world of quantum superpositions in our everyday lives is a phenomenon known as quantum decoherence. This process acts as a bridge between the quantum and classical worlds, explaining why the peculiar behaviors of particles remain hidden from our macroscopic experience. At the quantum level, particles such as electrons and photons can exist in multiple states simultaneously, a concept called superposition. Imagine a spinning coin that is both heads and tails at the same time. This dual existence persists until an observation is made, forcing the coin to settle on one side. Similarly, quantum particles hold various potential states, embodying a range of possibilities until they are measured or interacted with. However, unlike the isolated environment of a laboratory experiment, the real world is a complex web of interactions. Every particle is constantly interacting with countless others and with its surrounding environment. These interactions cause the delicate superpositions to break down, a process known as decoherence. Think of a delicate soap bubble floating in the air. While it can shimmer with vibrant colors when undisturbed, any slight touch or breeze causes it to pop and disappear. Decoherence works in a comparable way, disrupting the superposition and forcing particles into definite states. Decoherence explains why we don't see objects in superpositions in our daily lives. When a quantum system interacts with its environment, whether through collisions with air molecules, interactions with light, or other forms of disturbance, the superposition states become entangled with the environment. This entanglement effectively disperses the quantum information, making the superposition states unobservable and resulting in the classical behavior we are familiar with. Quantum decoherence not only explains the absence of observable superpositions in the macroscopic world, but also plays a crucial role in the development of quantum technologies. In quantum computing, for instance, maintaining coherent superpositions of qubits is essential for performing complex calculations. Decoherence poses a significant challenge, as it can disrupt the delicate quantum states needed for computation. Researchers are continually seeking ways to minimize decoherence, such as isolating quantum systems from environmental interactions, or using error-correcting codes to preserve quantum information. Another area where decoherence is pivotal is in the study of quantum entanglement. entangled particles maintain a correlation that persists even when separated by large distances. However, decoherence can degrade these entangled states, limiting the effectiveness of applications like quantum cryptography and teleportation. Understanding and controlling decoherence is therefore fundamental to advancing these technologies and harnessing the full potential of quantum mechanics. Beyond technology, decoherence has profound implications for our understanding of reality. It bridges the gap between the quantum and classical worlds, providing a framework that reconciles the probabilistic nature of quantum mechanics with the deterministic behavior of classical physics. This reconciliation helps explain why the macroscopic world appears orderly and predictable, despite the underlying quantum uncertainties. The study of decoherence also touches upon philosophical questions about the nature of observation and reality. It suggests that the act of measurement and interaction with the environment plays a crucial role in shaping the states of quantum systems. This interplay between the observer and the observed challenges traditional notions of objective reality, hinting at a more interconnected and dynamic universe. As research progresses, scientists continue to explore the nuances of decoherence, seeking innovative ways to control and exploit this phenomenon. Advances in material science, quantum control techniques, and theoretical models are paving the way for breakthroughs that could mitigate the effects of decoherence, enhancing the performance and reliability of quantum systems. These efforts not only push the boundaries of technology, but also expand our philosophical and scientific horizons, offering a more unified and coherent picture of reality. In summary, quantum decoherence is the key to understanding why the bizarre behaviors of the quantum world remain hidden from our everyday experiences. It acts as a guardian, preserving the classical order by dissipating the fragile superpositions that define the quantum realm. By unraveling the complexities of decoherence, we bridge the gap between the microscopic and macroscopic, unveiling the seamless continuity that underpins the fabric of reality. Quantum decoherence helps explain the transition from the quantum to the classical realm. With this in mind, let's now explore the quantum fields. If you peer into the fundamental fabric of the universe, you'll encounter a concept that redefines our understanding of reality: quantum fields. These fields are not just abstract mathematical constructs, but the very building blocks that compose everything around us. From the tiniest particles to the vast expanses of space, quantum fields form the underlying essence of all matter and energy. A quantum field is an entity that permeates all of space and time, with each type of particle corresponding to its own unique field. Imagine an invisible ocean stretching infinitely in every direction, with waves rippling through it continuously. These waves represent the excitations of quantum fields, manifesting as particles when observed. For instance, the electromagnetic field gives rise to photons, the particles of light, while the electron field produces electrons. This seamless interplay between fields and particles forms the foundation of what we perceive as the physical world. Unlike classical fields, which describe forces acting at a distance, quantum fields incorporate the principles of quantum mechanics, introducing a probabilistic nature to their behavior. This means that particles are not seen as isolated points, but as excitations within their respective fields, existing in a state of constant flux. The interactions between these fields dictate the fundamental forces of nature: electromagnetism, the strong and weak nuclear forces, and gravity, each playing a crucial role in shaping the universe. One of the most profound implications of quantum fields is their ability to explain the creation and annihilation of particles. In the quantum realm, particles can spontaneously appear and disappear, a phenomenon known as quantum fluctuations. These fleeting events occur within the vacuum of space, where energy briefly materializes into particle-antiparticle pairs, before vanishing again. This dynamic behavior underscores the ever-changing nature of quantum fields, where stability and change coexist in a delicate balance. Quantum field theory, QFT, is the framework that unites quantum mechanics with special relativity, providing a comprehensive description of how particles and fields interact. Through QFT, scientists can predict the outcomes of particle collisions, understand the behavior of fundamental forces, and explore the intricate connections between different types of particles. This theoretical foundation has led to remarkable advancements in physics, from the discovery of the Higgs boson to the development of technologies like semiconductors and lasers. A key feature of quantum fields is their inherent symmetry, which governs the conservation laws and interactions within the universe. Symmetries in quantum fields lead to the conservation of quantities such as energy, momentum, and charge, ensuring that these properties remain constant despite the dynamic interactions occurring at the quantum level. These symmetries also give rise to the fundamental forces, with each force associated with specific types of field interactions. For example, the electromagnetic force arises from the interactions of charged particles with the electromagnetic field, while the strong nuclear force binds protons and neutrons within atomic nuclei through the exchange of particles known as gluons. The concept of quantum fields also bridges the gap between particles and forces, revealing that they are two sides of the same coin. Particles are essentially excitations of their corresponding fields, and forces are mediated by the exchange of these excitations. This unified view simplifies our understanding of the interactions that govern the behavior of matter and energy, providing a coherent picture of the universe's fundamental workings. Moreover, quantum fields extend beyond our immediate perception, influencing phenomena that shape the cosmos on grand scales. For instance, the quantum fluctuations in the early universe played a pivotal role in the formation of galaxies and large-scale structures. These tiny irregularities in the quantum fields were amplified over time, leading to the vast and complex structures we observe today. This connection between quantum fields and cosmology highlights the profound impact that these fundamental entities have on both the microscopic and macroscopic realms. In addition to their role in particle physics and cosmology, quantum fields are integral to emerging technologies that promise to revolutionize our world. Quantum computing, for example, leverages the principles of quantum fields to perform computations at speeds unattainable by classical computers. By manipulating the quantum states of particles within their fields, quantum computers can process vast amounts of information simultaneously, tackling complex problems with unprecedented efficiency. Similarly, advancements in quantum communication and cryptography rely on the properties of quantum fields to ensure secure and reliable transmission of information. Despite their significance, quantum fields remain a topic of ongoing research and exploration. Scientists continue to refine their understanding of these fields, uncovering new insights into the nature of reality and the forces that shape it. The quest to unify quantum field theory with gravity, seeking a comprehensive theory of everything, exemplifies the relentless pursuit of knowledge that drives scientific progress. As our comprehension of quantum fields deepens, so too does our ability to harness their power, paving the way for innovations that will transform our lives and our understanding of the universe. In essence, quantum fields are the invisible scaffolding that constructs the tangible world we experience. They embody the dynamic interplay of particles and forces, orchestrating the intricate dance that defines existence at its most fundamental level. From the smallest particles to the vastest structures, quantum fields form the underlying essence of all matter and energy. By studying quantum fields, we gain a deeper appreciation for the complexity and elegance of the universe, recognizing that beneath the surface of everyday reality lies a vibrant and ever-evolving quantum landscape. Understanding quantum fields not only enhances our scientific knowledge but also enriches our philosophical perspective on reality. It reveals a universe that is both interconnected and dynamic, where the smallest particles and the vastest structures are unified by the fundamental principles of quantum mechanics. This realization fosters a sense of wonder and curiosity, inspiring us to continue exploring the mysteries of the quantum realm and uncovering the hidden truths that lie at the heart of existence. Quantum fields are a fundamental concept in modern physics, but we also need to understand another equation that's crucial to our understanding of the quantum world. This is the Dirac Equation. You may have heard of the Schrödinger equation, a fundamental component of quantum mechanics that describes how the quantum state of a physical system changes over time. However, to fully integrate quantum mechanics with the theory of relativity, a more advanced equation was needed. This is where the Dirac equation comes into play, serving as a pivotal bridge between quantum mechanics and Einstein's theory of relativity. Developed by the British physicist Paul Dirac in 1928, the Dirac equation extends the principles of quantum mechanics to accommodate the requirements of special relativity. While the Schrödinger equation successfully describes non-relativistic particles, it falls short when dealing with particles moving at speeds close to the speed of light. Dirac sought to create an equation that not only accounted for these high-velocity particles, but also incorporated the intrinsic spin of electrons, a fundamental property that classical mechanics could not explain. The Dirac equation accomplishes this by combining quantum mechanics with the principles of special relativity, resulting in a relativistic wave equation. Unlike its non-relativistic counterpart, the Dirac equation predicts the existence of antimatter, a concept that was revolutionary at the time. Antimatter consists of particles that have the same mass as their corresponding matter counterparts but opposite charges. For every particle described by the Dirac equation, there exists an antiparticle with identical mass and opposite charge. This prediction was later confirmed with the discovery of the positron, the antiparticle of the electron, in 1932. Mathematically, the Dirac equation is more complex than the Schrödinger equation. It involves the use of matrices and spinors, which are mathematical objects that account for the spin and relativistic effects of particles. Spin, a quantum property of particles, describes their intrinsic angular momentum and is essential for understanding the behavior of electrons in atoms. The inclusion of spin in the Dirac equation allows for a more accurate and comprehensive description of particle dynamics. One of the remarkable features of the Dirac equation is its ability to naturally incorporate both particles and antiparticles within the same framework. This unification suggests that the universe is fundamentally symmetric, with matter and antimatter existing in balanced pairs. The existence of antimatter has profound implications for our understanding of the universe, including questions about why there is more matter than antimatter, leading to the matter-antimatter asymmetry observed today. Beyond predicting antimatter, the Dirac equation also provides insights into the fine structure of atomic spectra. It explains the splitting of spectral lines observed in hydrogen atoms, which arises from the interaction between the electron's spin and its orbital motion around the nucleus. This interaction, known as spin-orbit coupling, was experimentally observed and is accurately described by the Dirac equation, highlighting its superiority over non-relativistic models. The Dirac equation also laid the groundwork for the development of quantum field theory, a framework that combines quantum mechanics with special relativity to describe the behavior of fields and particles. Quantum field theory is essential for understanding the interactions between fundamental particles, such as those mediated by the electromagnetic, weak, and strong nuclear forces. The success of the Dirac equation in unifying these theories underscores its significance in modern physics. In addition to its theoretical importance, the Dirac equation has practical applications in various fields of physics and technology. It is instrumental in the study of quantum electrodynamics, QED, which describes how light and matter interact. QED is one of the most accurately tested theories in physics, with predictions that align closely with experimental results. The precision of QED owes much to the foundational work of Dirac and his equation. Furthermore, the Dirac equation plays a crucial role in the exploration of topological insulators and other advanced materials in condensed matter physics. These materials exhibit unique electronic properties that arise from the interplay between their electronic structure and topological characteristics, phenomena that are deeply rooted in the principles described by the Dirac equation. Understanding these materials opens up new possibilities for developing innovative technologies, including quantum computing and spintronics. The Dirac equation challenges our perceptions of reality by introducing concepts that were previously unimaginable, such as antimatter. It invites us to reconsider the fundamental symmetries of the universe and the nature of particles and their interactions. The equation exemplifies the power of theoretical physics to predict new phenomena that extend beyond the realm of direct observation, shaping our understanding of the cosmos in profound ways. In summary, the Dirac equation is a cornerstone of modern physics, seamlessly integrating quantum mechanics with special relativity and introducing the concept of antimatter. Its ability to describe the behavior of particles at high velocities and account for intrinsic spin makes it indispensable for both theoretical exploration and practical applications. By bridging the gap between quantum mechanics and relativity, the Dirac equation not only enhances our understanding of the microscopic world, but also paves the way for advancements in technology and deepens our philosophical insights into the nature of reality. The Dirac equation revolutionized our understanding of the quantum world. Now we understand this, let's explore another important concept: quantum gravity. The universe is a stage where gravity and quantum phenomena coexist, yet no single theory currently accounts for both under all conditions. Quantum gravity seeks to merge general relativity, which describes gravity as the curvature of space-time, with quantum mechanics, the framework that explains the behavior of particles and forces at the smallest scales. This synthesis is essential for understanding extreme environments, such as the interiors of black holes or the universe in its earliest moments, where both strong gravitational fields and quantum effects play significant roles. General relativity has provided remarkably accurate predictions for phenomena on large scales, including the orbits of planets and the dynamics of galaxies. However, when applied to situations involving exceedingly small distances and high energies, such as the singularity at the center of a black hole, the smooth fabric of spacetime predicted by relativity breaks down. On the other hand, quantum mechanics excels at describing the probabilistic nature of particles and interactions, but does not naturally incorporate the gravitational force. The quest for quantum gravity is an attempt to develop a theory that can explain the behavior of all fundamental forces within a single coherent framework. Several approaches to quantum gravity have emerged over the past few decades. One prominent candidate is string theory, which proposes that the fundamental constituents of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can oscillate in different modes, with each mode corresponding to a different particle. String theory naturally incorporates gravity by predicting a particle known as the graviton, a massless excitation that mediates gravitational interactions. Although string theory offers a unified description of all forces, it requires additional spatial dimensions and involves complex mathematical structures that have yet to be tested directly through experiments. An alternative approach is loop quantum gravity, which attempts to quantize space-time itself. In this framework, space is composed of discrete units organized into a network of loops, known as spin networks. Rather than treating space-time as a continuous entity, loop quantum gravity suggests it has an atomic structure, which could prevent the formation of singularities, and resolve some of the infinities that appear in general relativity. While this approach retains many of the principles of relativity, it offers a radical rethinking of the nature of space and time at the smallest scales. Both string theory and loop quantum gravity have contributed valuable insights into the nature of the universe, even though neither has yet achieved the status of a complete theory of everything. Experimental evidence remains elusive because the energy scales at which quantum gravitational effects become significant are far beyond the reach of current technology. As a result, researchers often rely on indirect tests and theoretical consistency to assess the validity of these models. The implications of a successful quantum gravity theory extend far beyond academic interest. In cosmology, such a theory could illuminate the conditions of the early universe, providing a clearer picture of the events following the Big Bang. It may offer explanations for cosmic inflation, the rapid expansion that shaped the large-scale structure of the cosmos, and resolve paradoxes such as the black hole information loss problem, which challenges our understanding of how information is preserved in the universe. Furthermore, insights from quantum gravity might influence emerging technologies in ways that are not yet fully anticipated. A more complete understanding of the interplay between quantum mechanics and gravity could lead to advancements in precision measurement, quantum computation, and even new methods of communication. These practical outcomes underscore the broader significance of the theoretical work aimed at unifying these foundational aspects of physics. In summary, quantum gravity represents the ongoing effort to create a unified description of nature that harmonizes the principles of general relativity with those of quantum mechanics. It addresses the limitations of each framework when applied separately, aiming to provide a comprehensive account of phenomena across all scales. The universe, with its vast expanse and intricate structure, continues to challenge our understanding, and the pursuit of quantum gravity remains one of the most compelling and profound endeavors in modern physics. Quantum gravity is a fascinating area of research that seeks to unify our understanding of the universe at the smallest scales. Let's take this a step further and explore black holes and quantum information. The fascination with black holes has long spurred questions about the interplay between gravity and quantum mechanics. In the mid-1970s, Stephen Hawking revealed that black holes are not entirely black. Instead, they emit a faint radiation, now known as Hawking radiation. This discovery was groundbreaking, as it suggested that black holes could gradually lose mass and eventually evaporate, challenging the idea that nothing escapes their grasp. Hawking's theoretical work combined principles from general relativity with quantum field theory, showing that quantum effects near a black hole's event horizon allow particle-antiparticle pairs to form spontaneously. In some instances, one particle falls into the black hole while the other escapes into space, resulting in a net loss of mass for the black hole. This process introduces profound implications for our understanding of information, raising questions about whether the information contained in matter consumed by black holes is permanently lost or somehow preserved. The concept of quantum information becomes particularly significant in this context. Traditional views in quantum mechanics emphasize that information about a system's state is never destroyed. However, if black holes evaporate completely, what becomes of the detailed information about the matter that fell in? This apparent contradiction, known as the black hole information paradox, has sparked vigorous debate among physicists. Resolving the paradox requires reconciling the rules of quantum mechanics with those of gravitational collapse. Various proposals have emerged to address this challenge. Some theories suggest that information might be encoded in subtle correlations within Hawking radiation, effectively preserving the details of the original state despite the apparent loss. Other ideas propose that information could be stored on a hypothetical boundary known as the event horizon, a concept linked to the holographic principle. This principle posits that all the information contained within a volume of space can be represented on its boundary, reshaping our understanding of space, time, and information storage. Efforts to understand these processes are crucial not only for black hole physics, but also for the broader quest to unify the laws of quantum mechanics with gravity. The study of Hawking radiation and the associated information paradox has led to significant advances in theoretical physics, stimulating research into quantum gravity, string theory, and other unifying frameworks. Experimental evidence for Hawking radiation remains elusive due to its extremely weak nature relative to the cosmic background. Despite this, the theoretical implications continue to influence contemporary research. Observations of phenomena related to black holes, combined with advancements in high-energy astrophysics, may eventually offer indirect support for these groundbreaking ideas. Each new insight brings us closer to understanding the complex relationship between quantum processes and the macroscopic behavior of gravitational systems. The study of black holes and quantum information represents one of the most intriguing intersections of modern physics. It challenges us to rethink long-standing assumptions about the permanence of information and the ultimate fate of matter in extreme gravitational fields. By examining these mysterious objects, researchers are pushing the boundaries of knowledge and opening up new avenues for exploring the fundamental principles that govern the universe. In summary, the mystery of Hawking radiation and the black hole information paradox continues to inspire research into the deepest questions of physics. It bridges the gap between our understanding of gravity and quantum mechanics, and encourages ongoing efforts to develop a more complete theory that encompasses both realms. The ongoing investigation into these phenomena not only enriches our scientific perspective, but also propels us toward a more unified picture of nature's most fundamental forces. Black holes and quantum information are truly fascinating topics. Building on this, let's learn about quantum fluctuations. Space at first glance appears empty, an infinite void stretching in every direction, devoid of matter, energy, or motion. This classical view of emptiness, however, does not hold up under the scrutiny of quantum mechanics. Instead, what appears to be nothingness is a dynamic and restless sea of activity, teeming with fleeting bursts of energy and particle interactions. These ephemeral phenomena, known as quantum fluctuations, reveal that even the most barren regions of space are far from empty. Quantum fluctuations arise from the fundamental principles of quantum mechanics, particularly the Heisenberg uncertainty principle. This principle states that certain pairs of physical properties, such as energy and time, cannot both be precisely determined at the same moment. As a result, even in a perfect vacuum, where no particles or radiation should exist, tiny, short-lived fluctuations of energy can spontaneously occur. These fluctuations give rise to virtual particle-antiparticle pairs that briefly appear and annihilate each other before they can be detected. Though their existence is transient, their effects are profound, influencing both microscopic and cosmic scales. At the smallest scales, quantum fluctuations play a crucial role in shaping the structure of space itself. They are responsible for phenomena such as the Casimir Effect, where two closely placed conducting plates experience an attractive force due to the altered vacuum energy between them. This effect, which has been experimentally verified, demonstrates that quantum fluctuations exert measurable forces, reinforcing the idea that empty space is not truly empty. Beyond laboratory experiments, quantum fluctuations also have significant implications for the fundamental nature of the universe. In cosmology, they are believed to have played a key role in the earliest moments following the Big Bang. During a period known as cosmic inflation, the universe underwent an extremely rapid expansion, stretching tiny quantum fluctuations across vast cosmic distances. These fluctuations became the seeds for the large-scale structure of the universe, forming the foundation for galaxies, clusters, and other cosmic structures observed today. The imprint of these fluctuations can still be seen in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Another profound implication of quantum fluctuations emerges in the concept of vacuum energy. The cumulative effect of fluctuations across all possible quantum fields leads to what is known as vacuum energy, a theoretical energy that pervades all of space. In quantum field theory, this energy is predicted to be immense, yet its observed effect in the universe appears to be much smaller. This discrepancy, known as the cosmological constant problem, remains one of the biggest mysteries in theoretical physics. The cosmological constant, introduced by Einstein and later linked to dark energy, suggests that vacuum energy might be responsible for the accelerated expansion of the universe. If quantum fluctuations contribute to dark energy, they could hold the key to understanding the ultimate fate of the cosmos. Quantum fluctuations also have implications for black hole physics. When a black hole absorbs matter, it increases in mass and distorts the surrounding spacetime. However, due to quantum fluctuations near the event horizon, pairs of virtual particles can appear, with one falling into the black hole and the other escaping into space. This process, known as Hawking radiation, leads to a slow but inevitable evaporation of black holes over immense timescales. The role of quantum fluctuations in this mechanism demonstrates their significance in reconciling quantum mechanics with gravity, hinting at deeper connections between these two fundamental forces. In addition to their theoretical importance, quantum fluctuations have technological applications, particularly in the development of quantum computing and precision measurements. Quantum fluctuations introduce noise into delicate quantum systems, posing both challenges and opportunities for quantum information processing. While fluctuations can disrupt computations, researchers are exploring ways to harness them for tasks such as quantum sensing and metrology, where they could enable unprecedented levels of measurement precision. Despite their significance, quantum fluctuations remain a subject of deep scientific inquiry. While their effects are well documented, their full implications for the fabric of reality are still being explored. Some theories suggest that fluctuations might even play a role in generating mass, influencing the Higgs field, which gives particles their mass. Others propose that fluctuations could provide insights into the nature of space-time itself, potentially pointing toward a quantum theory of gravity. The concept of quantum fluctuations also raises intriguing philosophical questions about the nature of existence. If empty space is never truly empty, then what defines reality at its most fundamental level? The distinction between something and nothing becomes blurred, suggesting that the very fabric of the universe is dynamic and ever-changing. This perspective challenges traditional notions of void and substance, pushing the boundaries of human understanding. Recent advancements in observational astrophysics have provided indirect evidence supporting the influence of quantum fluctuations on cosmic evolution. Studies of distant supernovae, gravitational waves, and the large-scale distribution of galaxies all point to the effects of vacuum energy. Moreover, high-precision experiments, such as those conducted at particle accelerators, continue to probe the quantum nature of empty space, seeking to uncover the deeper mechanisms governing fluctuations and their impact on the universe. While quantum fluctuations are typically considered short-lived and localized, some theories explore the possibility that they could lead to large-scale effects, such as the spontaneous creation of entire universes. Some cosmologists propose that fluctuations in a quantum vacuum could trigger inflationary events similar to the Big Bang, potentially giving rise to parallel universes. This notion, though speculative, aligns with certain interpretations of quantum mechanics that suggest reality is shaped by probability and randomness at its core. In experimental physics, efforts to directly manipulate vacuum fluctuations are ongoing. The study of quantum optics, for instance, explores ways to control fluctuations to enhance optical systems, leading to innovations in laser technology and quantum communication. By refining our understanding of how these fluctuations operate, researchers are unlocking new possibilities for technological applications that were once thought to belong solely to the realm of theoretical physics. Quantum fluctuations remind us that reality is far more intricate than it appears at first glance. What seems like empty space is, in fact, a constantly shifting landscape of energy and activity, shaping the universe in ways both subtle and profound. They are responsible for some of the most fundamental processes in nature, influencing everything from atomic interactions to the expansion of the cosmos. Though their effects often go unnoticed in everyday life, they are essential to the structure and evolution of the universe itself. In the pursuit of a deeper understanding of these fluctuations, scientists continue to refine their theories, conduct experiments, and push the limits of knowledge. Whether through their role in shaping the early universe, influencing black hole behavior, or driving technological advancements, quantum fluctuations remain a crucial aspect of modern physics. Quantum fluctuations are a testament to the intricate nature of the quantum world. But there's another mysterious aspect of the universe that's closely tied to quantum mechanics: dark matter. Let's explore this intriguing topic next. Dark matter and quantum mechanics. Dark matter remains one of the most perplexing mysteries in modern physics. It does not emit, absorb, or reflect light, making it entirely invisible to conventional telescopes. Yet its presence is inferred through its gravitational effects on galaxies, galaxy clusters, and cosmic structures. Despite decades of research, scientists have yet to determine its exact nature. While dark matter is often discussed in the context of astrophysics and cosmology, quantum mechanics might hold the key to understanding its fundamental properties. The existence of dark matter was first proposed to explain discrepancies between observed galactic rotations and predictions based on visible matter alone. Astronomers found that the outer regions of galaxies rotate at speeds that defy the expectations set by Newtonian and Einsteinian gravity. If only visible matter were responsible for the gravitational pull, stars at the edges of galaxies should move more slowly than those near the center. Instead, they maintain nearly constant speeds, suggesting the presence of an unseen mass, one that does not interact with light, but exerts a gravitational influence. Quantum mechanics, the framework governing the behavior of particles at microscopic scales, may provide insights into dark matter's elusive nature. Various theoretical candidates for dark matter particles have been proposed, many of which rely on quantum principles. One of the leading hypotheses involves weakly interacting massive particles, WIMPs, which are thought to interact primarily through gravity and the weak nuclear force. If WIMPs exist, they could be detected through rare interactions with ordinary matter, an endeavor that has driven the construction of sensitive underground detectors worldwide. Another possibility is that dark matter consists of axions, hypothetical ultra-light particles predicted by certain quantum field theories. Unlike WIMPs, axions would interact even more weakly with ordinary matter, making them even harder to detect. These particles could form a cosmic field that oscillates across space, subtly influencing the behavior of photons and other particles. Experiments using strong magnetic fields, such as the Axion Dark Matter Experiment ADMX, aim to uncover these elusive particles by detecting their predicted interactions with electromagnetic waves. Beyond these candidates, there is growing interest in the idea that dark matter may arise from modifications to quantum mechanics itself. Some researchers suggest that dark matter could be an emergent phenomenon resulting from the collective behavior of quantum fields on cosmic scales. This perspective challenges the assumption that dark matter is a distinct type of particle, and instead proposes that quantum effects manifest in ways that mimic the presence of unseen mass. Quantum mechanics also plays a role in alternative explanations for dark matter's effects. One such idea is that modifications to gravity, rather than an unseen mass, could account for the observed galactic motions. Theories like modified Newtonian dynamics, MOND, attempt to adjust gravitational laws at large distances, reducing the need for dark matter entirely. However, these modifications struggle to explain the full range of cosmic observations, particularly in galaxy clusters and large-scale cosmic structures, where dark matter provides a more consistent explanation. The intersection of quantum mechanics and dark matter extends into the study of quantum fluctuations and vacuum energy. Quantum field theory predicts that empty space is not truly empty, but filled with fluctuations that constantly produce and annihilate virtual particles. Some researchers speculate that these fluctuations could contribute to dark matter-like effects, creating a form of quantum dark matter that influences large-scale cosmic dynamics. If this connection holds, it could reshape our understanding of both quantum physics and cosmology. One intriguing avenue of research involves the idea that dark matter may interact with itself, or with ordinary matter, through unknown quantum forces. While dark matter is often assumed to be nearly non-interacting, some models suggest that it could form structures or even have complex internal dynamics governed by hidden quantum interactions. These self-interacting dark matter models propose that dark matter particles may exchange unknown force carriers, creating effects that could be detected through subtle changes in cosmic structure formation. The search for direct evidence of dark matter's quantum nature is ongoing. Particle accelerators, such as the Large Hadron Collider, LHC, aim to create dark matter particles by colliding high-energy protons, hoping to detect missing energy signatures that hint at their existence. Meanwhile, astrophysical observations, including studies of gravitational lensing and cosmic microwave background fluctuations, continue to refine our understanding of where and how dark matter exerts its influence. Quantum entanglement has also been suggested as a possible key to unlocking dark matter's mysteries. Some speculative theories propose that dark matter could be connected across vast distances through entangled quantum states, leading to non-local effects that influence cosmic evolution. While such ideas remain highly theoretical, they offer novel ways of thinking about the role of quantum mechanics in shaping the universe. Another speculative but intriguing possibility is that dark matter could be composed of primordial black holes, formed in the early universe. These black holes, if small enough, would not emit detectable Hawking radiation and could remain hidden within galaxies. While not a quantum mechanical explanation in itself, the study of these objects involves quantum gravity principles, since their formation and properties depend on conditions present in the first moments after the Big Bang. The relationship between dark matter and quantum mechanics may also have practical implications for future technologies. Understanding the quantum properties of dark matter could lead to advancements in quantum sensing, where highly precise instruments detect minute gravitational effects. Quantum-enhanced detection methods, including interferometry and entangled particle experiments, may eventually provide the sensitivity needed to directly observe dark matter interactions. Despite decades of effort, the precise connection between dark matter and quantum mechanics remains an open question. Theories abound, ranging from well-established particle physics models to more radical ideas that challenge conventional notions of space, time, and mass. What is clear, however, is that solving the mystery of dark matter requires integrating quantum principles with our understanding of cosmology and gravity. If dark matter is ultimately found to be a quantum phenomenon, it would mark a profound shift in our understanding of the universe's composition. Such a discovery would bridge the gap between the smallest scales of quantum physics and the largest structures in the cosmos, unifying disparate areas of science in a way that has long been sought. Whether through direct detection of particles, novel quantum interactions, or new principles emerging from theoretical research, the search for dark matter remains one of the most significant scientific pursuits of our time. While current experiments push the boundaries of detection, new theoretical frameworks continue to emerge, each offering a different perspective on how dark matter and quantum mechanics might be linked. As technology advances and our observational tools become more refined, the answers to these fundamental questions may finally come into focus. Dark matter is a fascinating mystery that lies at the intersection of quantum mechanics and cosmology. To add another level of understanding, let's discuss the quantum nature of time. Let's explore this mind-bending concept next. Time in everyday experience moves forward in a steady, predictable flow. Clocks tick, seasons change, and past events remain fixed, while the future remains uncertain. This perception aligns with classical physics, where time is treated as an absolute dimension, progressing uniformly regardless of circumstances. However, when examined at the quantum level, time behaves in ways that defy common intuition. Unlike space, which is divided into discrete quanta and various quantum gravity models, time remains a puzzling concept that may not be as continuous as it appears. In classical physics, Isaac Newton described time as an independent, universal backdrop against which events unfold. This idea was challenged by Albert Einstein's theory of relativity, which demonstrated that time is not absolute, but instead intertwined with space in a four-dimensional fabric called spacetime. According to relativity, time can stretch or contract depending on the observer's speed and the presence of strong gravitational fields. This phenomenon, known as time dilation, has been confirmed through experiments involving high-speed travel and the effects of gravity near massive objects. While relativity provides a well-tested description of time on large scales, quantum mechanics introduces further complexities when examining time at microscopic levels. Quantum mechanics governs the behavior of particles at the smallest scales, where uncertainty and probability dictate outcomes rather than fixed, deterministic laws. If time behaves differently at these scales, then our understanding of causality and temporal evolution may need to be re-examined. While space can be divided into discrete quanta in some quantum gravity theories, time remains continuous in quantum mechanics. Unlike position or momentum, time is not represented by an operator in standard quantum theory, making its role fundamentally different from other physical quantities. Some interpretations of quantum mechanics suggest that time may not flow in a straightforward manner at the smallest scales. The concept of superposition allows particles to exist in multiple states simultaneously, until measured, raising questions about whether time itself could exist in a superposition of different states. If so, what would that imply for our experience of time at macroscopic scales? Could time itself be an emergent phenomenon rather than a fundamental aspect of reality? Quantum entanglement further complicates the nature of time. When two particles become entangled, measuring one instantaneously affects the state of the other, regardless of distance. This effect appears to transcend conventional notions of time and causality, leading some physicists to propose that time may emerge from a deeper quantum reality rather than being a fundamental property of the universe. Another approach to understanding time in quantum mechanics involves the Wheeler-DeWitt equation, an attempt to describe quantum gravity. This equation, proposed by John Wheeler and Bryce DeWitt, removes time as a separate parameter, suggesting that the universe at a fundamental level may be timeless. According to this view, time as we perceive it might emerge only in certain conditions, much like temperature emerges from the collective motion of molecules, rather than being a fundamental property of individual atoms. Greater than. The idea that time emerges rather than existing fundamentally aligns with some interpretations of quantum mechanics that treat reality as a set of evolving correlations rather than events occurring along a rigid timeline. Quantum processes do not necessarily have a preferred direction, unlike macroscopic time, which moves irreversibly from past to future. This contrast raises the question of whether the arrow of time, the one-way progression we experience, is an emergent property rather than a fundamental aspect of nature. In thermodynamics, the second law states that entropy or disorder always increases in a closed system, giving time its apparent direction. However, quantum mechanics operates with time-reversible equations, meaning that at the quantum level there is no preferred direction for time. This discrepancy suggests that the arrow of time might result from interactions at a macroscopic level, rather than being inherent in fundamental laws. Some theories suggest that time may be quantized, meaning it exists in discrete units, rather than flowing smoothly. In quantum gravity models such as loop quantum gravity, space-time itself is thought to be composed of tiny, indivisible units, leading to speculation that time, too, might have a smallest possible increment. If true, then time would not be a continuous stream, but rather a series of discrete moments, much like frames in a film. Another intriguing hypothesis is that time could be an illusion created by human perception. Certain interpretations of quantum mechanics propose that reality consists of a vast collection of static states, and what we experience as time is simply our consciousness moving through these states in a particular order. This idea is similar to the block universe concept in relativity, where past, present, and future all coexist, and the perception of time flowing is merely an artifact of human experience. Greater than experimental efforts to probe the quantum nature of time include studying ultra-cold atomic clocks, which measure time with extraordinary precision. These clocks allow researchers to test whether time behaves differently under extreme conditions, such as near black holes or at quantum scales. Some proposals even suggest that quantum mechanics and general relativity might manifest measurable discrepancies in timekeeping, which could offer insights into how time functions at a fundamental level. If time is an emergent property rather than a fundamental aspect of reality, then understanding its origins could provide deeper insights into the nature of space, matter, and the universe itself. It could also impact fields such as quantum computing, where time-dependent processes play a crucial role in information processing and coherence. A deeper understanding of time's quantum nature could lead to advancements in precision measurement, fundamental physics, and even new perspectives on reality. The relationship between time and measurement in quantum mechanics also raises philosophical questions about free will and determinism. If quantum mechanics allows for superpositions of different time states, does this imply that multiple versions of events exist simultaneously? Could our perception of time be limited by the constraints of measurement, much like how observing a quantum particle forces it into a definite state? These questions challenge our classical assumptions about cause and effect, prompting further exploration into the nature of time itself. Time, whether fundamental or emergent, remains one of the greatest puzzles in physics. The search for a unified theory of quantum gravity, which could reconcile general relativity with quantum mechanics, might ultimately reveal the true nature of time, whether it is continuous or discrete, an illusion, or an intrinsic part of reality. Its mysteries continue to drive theoretical and experimental inquiry. Current research continues to push the boundaries of our understanding. Advances in quantum simulations, gravitational wave astronomy, and high-precision timekeeping offer new ways to explore the relationship between time and quantum mechanics. As experimental techniques improve, the possibility of uncovering new aspects of time, whether through quantum entanglement, space-time quantization, or entirely new physics, remains open. Greater than. The quantum nature of time is a truly mind-bending concept that challenges our everyday perceptions. But there's another fascinating quantum phenomenon that demonstrates the peculiar behavior of empty space: the Casimir Effect. The Casimir Effect is one of the most striking demonstrations that empty space is not truly empty. It reveals that even in a vacuum, where no matter or radiation should be present, measurable forces can arise purely from quantum fluctuations. This phenomenon, first predicted by Dutch physicist Hendrik Casimir in 1948, is a direct consequence of quantum field theory and has been experimentally verified multiple times. The Casimir Effect not only provides insight into the nature of quantum vacuum energy, but also has implications for nanotechnology, fundamental physics, and the potential unification of quantum mechanics and gravity. The Casimir Effect describes the force that arises between two parallel, uncharged conducting plates placed in a vacuum. According to classical physics, there should be no force acting between them, as no particles or radiation are present to exert pressure. However, quantum mechanics tells a different story. Due to the nature of quantum fluctuations, space is never truly empty. Instead, it is filled with virtual particles, pairs of particles, and antiparticles that constantly appear and disappear in accordance with the Heisenberg uncertainty principle. These virtual particles create a background energy known as vacuum energy, which exists everywhere, even in seemingly empty space. When two plates are placed close together, they limit the wavelengths of virtual particles that can exist between them. Outside the plates, however, all wavelengths are allowed. This imbalance in energy density results in a net force that pushes the plates toward each other. The closer the plates are, the stronger the force, making the Casimir Effect more pronounced at microscopic scales. The strength of this force is incredibly small, yet it has been measured with high precision in laboratory experiments. The first definitive experimental confirmation came in 1997, when physicists used a delicate torsion balance to detect the attractive force predicted by Casimir's calculations. Since then, more sophisticated methods have refined these measurements, confirming the predictions of quantum field theory with remarkable accuracy. The Casimir Effect is often viewed as a direct consequence of quantum field theory, the framework that describes how particles and forces interact at the quantum level. It highlights the role of zero-point energy, the lowest possible energy that a quantum system can have. Even in the absence of real particles, the vacuum still possesses energy due to these fluctuations. While this energy cannot be harnessed in the way classical energy sources are, its presence is undeniable and has observable effects. Beyond being a theoretical curiosity, the Casimir Effect has practical implications. In nanotechnology and microelectromechanical systems, MEMS, where components operate at extremely small scales, Casimir forces can influence device behavior. As technology shrinks, these forces become significant enough to cause components to stick together, an effect known as stiction. Engineers must account for this quantum force when designing nanoscale devices, either by mitigating its impact or using it to their advantage in novel applications. One of the most exciting areas of research is the possibility of controlling or even reversing the Casimir Effect. While it is traditionally an attractive force, certain configurations of materials and electromagnetic properties could create repulsive Casimir forces. This has led to speculation about potential applications in frictionless nanomachines and quantum levitation, where objects might be suspended without direct physical contact. The Casimir Effect also has implications for cosmology and the nature of dark energy. The vacuum energy responsible for the Casimir force is related to the concept of the cosmological constant, a term introduced by Einstein and later linked to the accelerated expansion of the universe. If vacuum fluctuations contribute to dark energy, understanding the Casimir Effect at deeper levels could provide clues about the forces driving cosmic acceleration. Another intriguing possibility is that the Casimir effect might play a role in future propulsion systems. Some speculative ideas suggest that manipulating vacuum energy could lead to propulsion mechanisms that do not rely on traditional fuel sources. While such concepts remain highly theoretical, the ability to harness vacuum fluctuations in novel ways could open new avenues for space travel and advanced engineering. Despite its well-established experimental foundation, the Casimir effect continues to be an area of active research. Scientists explore how it behaves in different geometries, with varying materials and under extreme conditions such as high temperatures or strong gravitational fields. Understanding how the effect scales in different environments may offer new insights into the fundamental nature of quantum vacuum energy and its role in shaping the universe. The connection between the Casimir effect and quantum gravity is another area of ongoing exploration. Some theories suggest that vacuum fluctuations could be linked to space-time curvature, potentially offering a pathway toward unifying quantum mechanics and general relativity. While no definitive breakthroughs have been made, the fact that a force can emerge from empty space challenges conventional notions of how forces and energy operate at fundamental levels. In addition to its role in physics and engineering, the Casimir effect raises philosophical questions about the nature of nothingness. Classical physics envisioned a vacuum as an empty void, devoid of properties or influence. Quantum mechanics, however, paints a picture of a vacuum teeming with activity, where energy fluctuations constantly shape the interactions of matter and forces. This shift in perspective has profound implications for our understanding of reality, suggesting that even the most seemingly empty spaces are filled with dynamic quantum processes. Efforts to further probe the Casimir effect include high-precision experiments using microcantilevers and atomic force microscopes, which allow for controlled measurements at nanometer scales. Advances in material science have also enabled the exploration of exotic materials, such as metamaterials, which could manipulate Casimir forces in unprecedented ways. These advancements pave the way for potential breakthroughs in quantum technologies, where vacuum fluctuations might be used for innovative purposes. While the Casimir effect remains a primarily theoretical and experimental topic, its broader implications extend into multiple domains of science. From fundamental physics to cutting-edge nanotechnology, it represents one of the most compelling demonstrations of quantum mechanics at work. It challenges long-held assumptions about the nature of space and energy, providing a glimpse into the deeper workings of the quantum world. Whether through its influence on microscopic engineering, its potential role in cosmic phenomena, or its connections to the mysteries of quantum gravity, the Casimir effect continues to be an important area of study. Its existence serves as a reminder that even in what seems like nothingness, the rules of quantum mechanics ensure that something is always happening, shaping the universe in ways both subtle and profound. Greater than. The Casimir effect is a fascinating demonstration of the strange behavior of empty space in the quantum realm, but there's another crucial concept in quantum physics that helps explain the fundamental interactions in the universe. Let's explore the role of symmetry in quantum physics next. The role of symmetry in quantum physics. Arrangement and order define much of the natural world, from the intricate patterns of a snowflake to the structured orbits of planets around the sun. In quantum physics, symmetry plays an even deeper role, governing the fundamental laws that dictate how particles interact, move, and evolve. It is not just an aesthetic property, but a guiding principle that helps physicists uncover the rules governing the smallest scales of reality. In classical mechanics, symmetry often refers to physical transformations that leave a system unchanged. A perfect sphere looks the same no matter how it is rotated, and a mirrored reflection of a right triangle retains the same angles and side ratios. In quantum mechanics, however, symmetry takes on a more profound meaning. influencing the conservation of quantities such as energy, momentum, and electric charge. One of the most significant contributions to the understanding of symmetry in physics comes from Emmy Noether, a mathematician whose theorem revealed a deep connection between symmetry and conservation laws. Noether's theorem states that for every continuous symmetry in nature, there is a corresponding conserved quantity. If the laws of physics remain unchanged under time shifts, energy is conserved. If they remain unchanged under spatial shifts, momentum is conserved. If they remain unchanged under rotational shifts, angular momentum is conserved. These relationships form the backbone of quantum theory, ensuring that fundamental interactions obey strict mathematical rules. Greater than. In quantum mechanics, symmetry is present in the behavior of wave functions, the mathematical descriptions of particles and their possible states. Certain symmetries in these wave functions determine how particles interact with forces and one another. For example, the Pauli exclusion principle, which states that two identical fermions, such as electrons, cannot occupy the same quantum state, arises from symmetry considerations in their wave functions. This principle is crucial in explaining the structure of atoms and the stability of matter. Another key example of symmetry in quantum physics is gauge symmetry, which underlies the standard model of particle physics. Gauge symmetries dictate the fundamental forces, electromagnetic, weak, and strong nuclear interactions by ensuring that physical laws remain consistent under specific mathematical transformations. These symmetries help define how particles like electrons and quarks behave and interact, leading to the discovery of force-carrying particles such as photons, W and Z bosons, and gluons. One of the most striking manifestations of symmetry in quantum physics is the concept of particle-antiparticle pairs. For every particle, there exists an antiparticle with opposite charge but otherwise identical properties. This symmetry, known as charge parity (CP symmetry), suggests that the universe should have equal amounts of matter and antimatter. However, observations indicate that matter vastly outnumbers antimatter, leading to ongoing research into whether small symmetry-breaking effects could explain this imbalance. Supersymmetry, a theoretical extension of the Standard Model, proposes an even deeper form of symmetry, linking particles that differ in spin. It predicts that for every known particle, there exists a heavier superpartner with a different spin property. While no direct evidence for supersymmetry has been found, it remains an active area of investigation, as it could help explain the nature of dark matter and unify fundamental forces. Beyond individual particles, symmetry plays a critical role in quantum field theory, where particles and forces are described as excitations of underlying fields. These fields obey symmetry principles that determine how interactions occur. The Higgs mechanism, responsible for giving mass to particles, emerges from the breaking of a fundamental symmetry in the Higgs field. The discovery of the Higgs boson in 2012 confirmed this theory, reinforcing the importance of symmetry in explaining particle properties. Symmetry also plays a fundamental role in quantum computing, where the stability of quantum bits, qubits, often depends on preserving or manipulating symmetrical states. Certain quantum error correction codes exploit symmetry to protect information from decoherence, ensuring more reliable quantum computations. Research into topological quantum computing further explores how symmetrical properties of matter could be used to build fault-tolerant quantum systems. In condensed matter physics, symmetry explains the behavior of exotic materials, including superconductors and topological insulators. In superconductors, electrons form pairs that move in a highly ordered manner, allowing electrical currents to flow without resistance. The symmetry properties of these electron pairs define the conditions under which superconductivity emerges and how it can be controlled. Similarly, topological insulators exhibit unique surface conductivity due to symmetry-protected quantum states, leading to potential applications in next-generation electronics. Another area where symmetry plays a vital role is in quantum cosmology. The early universe is thought to have undergone symmetry-breaking events that shaped its evolution. For example, during cosmic inflation, rapid expansion may have caused certain symmetries in fundamental fields to break, leading to the formation of matter structures. Understanding these processes could shed light on the fundamental origins of the universe. Experimental tests of symmetry violations provide valuable insights into the limits of known physics. The observation of CP violation, where tiny asymmetries between matter and antimatter interactions occur, has provided clues about why matter dominates the universe. Similarly, precise measurements of electron-electric dipole moments test whether certain symmetries hold or break at subatomic levels, potentially revealing new physics beyond the standard model. Despite its central role in modern physics, symmetry is not always perfect. Nature exhibits spontaneous symmetry breaking, where an underlying symmetry exists but is not observed in certain conditions. This phenomenon explains why certain particles acquire mass while others do not, or why certain materials change properties at different temperatures. The study of symmetry breaking has led to groundbreaking discoveries, including the Higgs boson and the mechanisms behind phase transitions in condensed matter systems. From fundamental forces to cutting-edge technologies, symmetry remains a guiding principle in quantum physics. It structures the laws that govern particles, shapes the interactions of forces, and provides insight into the nature of the universe itself. As experimental techniques improve and theoretical models evolve, the role of symmetry continues to expand, uncovering deeper connections between the known and unknown aspects of reality. While symmetry provides order, its breaking is equally important, leading to new phenomena and revealing hidden structures within quantum systems. Understanding both symmetry and its violations offers a richer perspective on the fundamental nature of matter, energy, and the interactions that define the physical world. Future discoveries may refine or even revolutionize our understanding of these symmetries, shedding light on the remaining mysteries of quantum physics. Symmetry is a crucial concept that helps explain the fundamental interactions in the quantum world. Let's now explore a groundbreaking development in quantum physics that's transforming the way we process information: quantum computing. Computers have transformed nearly every aspect of modern life, from communication and data processing to scientific research and artificial intelligence. Classical computers, which rely on bits to process information as either zeros or ones, have grown exponentially more powerful over the decades, following Moore's law. However, as transistors shrink to atomic scales, the limitations of classical computing become apparent. To overcome these limits, researchers have turned to quantum computing, a field that harnesses the principles of quantum mechanics to process information in ways that classical computers cannot. Unlike classical bits, which exist in a binary state, quantum computers use quantum bits or qubits. Qubits can exist in multiple states simultaneously, thanks to a principle known as superposition. This allows quantum computers to perform vast numbers of calculations at once, exponentially increasing their computational power for certain types of problems. Instead of evaluating one possibility at a time, as classical computers do, quantum systems explore many solutions simultaneously, making them particularly suited for tasks such as optimization, cryptography, and complex simulations. Another key property of quantum computing is entanglement. When qubits become entangled, the state of one qubit is instantaneously correlated with the state of another, regardless of distance. This phenomenon enables quantum computers to process and transfer information in ways that classical systems cannot replicate. Entanglement enhances computational efficiency, allowing quantum algorithms to solve certain problems much faster than their classical counterparts. Quantum computers also leverage interference, a principle that allows qubits to reinforce correct solutions while canceling out incorrect ones. By carefully designing quantum algorithms, researchers can guide computations toward the most probable and accurate outcomes. This capability is particularly valuable in fields that require solving complex probabilistic problems, such as machine learning, drug discovery, and material science. Greater than. One of the most famous quantum algorithms, Shor's algorithm, demonstrates the superiority of quantum computing in specific tasks. This algorithm efficiently factors large numbers, a problem that classical computers struggle with as the numbers grow larger. The ability to quickly factor numbers threatens traditional encryption methods, such as RSA cryptography, which relies on the difficulty of factoring large primes. Quantum-resistant encryption methods are already being developed to address this potential vulnerability. Another significant quantum algorithm is Grover's algorithm, which accelerates search processes. Classical computers must check each entry in an unsorted database one by one, but Grover's algorithm enables quantum computers to find the correct entry much faster by exploiting quantum superposition. This speed-up has implications for database management, artificial intelligence, and cybersecurity. Despite its promise, quantum computing faces substantial technical challenges. One of the biggest obstacles is qubit stability. Unlike classical bits, which maintain their states reliably, qubits are highly susceptible to environmental interference. This fragility, known as quantum decoherence, can cause errors in calculations, making it difficult to maintain coherent quantum states for extended periods. To address decoherence, researchers are developing quantum error correction techniques. Unlike classical error correction, which relies on redundancy, quantum error correction must preserve delicate quantum states without directly measuring them. Techniques such as surface codes and topological qubits offer potential solutions, but implementing them requires significant advancements in hardware and control systems. Greater than. Currently, there are several competing approaches to building quantum computers, each with its own advantages and challenges. Superconducting qubits used by companies like IBM and Google operate at extremely low temperatures to minimize decoherence. Trapped ion quantum computers, developed by researchers at institutions such as IonQ, use individual atoms as qubits, offering high stability and precision. Other approaches, including photonic and topological quantum computing, explore different methods of encoding and manipulating quantum information. The race to build practical quantum computers has attracted major investments from both governments and private companies. Tech giants such as Google, IBM, Microsoft, and startups like Rigetti and D-Wave are working to develop scalable quantum processors. Governments around the world are funding quantum research initiatives, recognizing the potential impact of quantum computing on national security, industry, and scientific discovery. One of the most anticipated milestones in quantum computing is achieving quantum supremacy, the point at which a quantum computer can solve a problem that is practically impossible for a classical computer to complete in a reasonable amount of time. In 2019, Google announced that its quantum processor, Sycamore, had achieved this milestone by performing a specific calculation in minutes that would take the most powerful classical supercomputer thousands of years. While this demonstration was highly specialized and not yet practical for real-world applications, it marked a significant step forward in the field. The potential applications of quantum computing extend far beyond cryptography and number factoring. In medicine, quantum computers could revolutionize drug discovery by simulating molecular interactions at an unprecedented level of detail. Classical computers struggle to model the quantum behavior of complex molecules, but quantum computers, operating under the same principles, could provide insights that accelerate the development of new treatments. Greater than. In materials science, quantum computers could help design new materials with specific properties by simulating atomic structures with extreme precision. This capability could lead to advancements in superconductors, energy-efficient batteries, and next-generation electronics. Financial institutions are also exploring quantum computing for optimization problems. Portfolio management, risk assessment, and fraud detection involve analyzing massive data sets and finding optimal solutions under complex constraints. Quantum algorithms could enhance decision-making in these areas, providing faster and more accurate predictions. Another promising application lies in artificial intelligence and machine learning. Quantum computing could enhance machine learning models by accelerating data processing and improving pattern recognition. While classical AI systems rely on vast amounts of computational power, quantum algorithms could significantly reduce the time required for training complex neural networks. Despite the excitement, it is important to recognize that practical, large-scale quantum computers are still in the early stages of development. Many technical hurdles remain, including increasing the number of qubits while maintaining error correction, improving coherence times, and developing scalable hardware architectures. The transition from experimental quantum processors to commercially viable quantum computing solutions will likely take years, if not decades. In the meantime, hybrid approaches combining classical and quantum computing are being explored. Quantum-inspired algorithms, which mimic certain aspects of quantum mechanics without requiring a full quantum system, are already being used in industries such as logistics, chemistry, and finance. These intermediate steps provide valuable insights while full-scale quantum computing technology continues to evolve. Another challenge is the need for specialized software to leverage quantum computing effectively. Unlike classical programming, quantum computing requires new algorithms and methods of thinking. Companies and research institutions are developing quantum programming languages and platforms, such as Qiskit, Cirq, and Quipper, to make quantum computing more accessible to developers. As research progresses, quantum computing is poised to become one of the most disruptive technologies of the coming decades. While classical computing will not be replaced, quantum computers will complement traditional systems, handling specific tasks that are computationally infeasible with current hardware. The impact of quantum computing will likely be felt across multiple industries, from science and technology to finance and national security. Ultimately, quantum computing represents a fundamental shift in how information is processed. By harnessing the principles of quantum mechanics, these machines offer the potential to solve problems that are beyond the reach of even the most advanced classical supercomputers. Quantum computing is a revolutionary field that promises to transform the way we process information. Let's extend this technology and discuss quantum cryptography. Cryptography has always been at the heart of secure communication, protecting sensitive information from prying eyes. From ancient ciphers to modern encryption algorithms, the methods used to encode messages have evolved alongside technology. However, the rise of quantum computing threatens the very foundations of classical cryptographic security. To counter this potential vulnerability, researchers have turned to quantum cryptography, a field that leverages the principles of quantum mechanics to create theoretically unbreakable encryption. Classical cryptography relies on mathematical complexity to secure data. Algorithms such as RSA and ECC, elliptic curve cryptography, depend on the difficulty of solving certain mathematical problems, such as prime factorization or discrete logarithms. These problems are computationally demanding for classical computers, making decryption without the proper key practically impossible. However, quantum computers, using Shor's algorithm, could factor large numbers exponentially faster than classical computers, rendering traditional encryption methods obsolete. Quantum cryptography offers a fundamentally different approach. Instead of relying on mathematical difficulty, It uses the inherent properties of quantum mechanics to ensure security. One of the most promising techniques is quantum key distribution, QKD, a method that enables two parties to generate and share a cryptographic key in a way that guarantees its secrecy. The most well-known QKD protocol is BB84, developed by Charles Bennett and Gilles Broussard in 1984. BB84 operates by encoding information onto individual photons, the fundamental particles of light. These photons are transmitted between two parties, traditionally called Alice and Bob, using randomly chosen quantum states. Due to the principles of quantum mechanics, any attempt by an eavesdropper, often called Eve, to intercept or measure these photons will inevitably disturb their state, alerting Alice and Bob to the intrusion. This property, known as the observer effect, ensures that any unauthorized attempt to access the key results in detectable anomalies, allowing the communication to be either abandoned or rerun until a secure exchange is achieved. Unlike classical encryption, where an intercepted key can be copied without detection, QKD ensures that any interception is immediately noticeable. This makes it theoretically immune to passive eavesdropping, where attackers secretly monitor transmissions without altering them. By detecting interference, Alice and Bob can discard compromised keys and only use those that remain secure. Beyond QKD, quantum cryptography explores other methods of securing communication. One promising approach is quantum entanglement-based encryption. When two particles become entangled, their states remain correlated no matter how far apart they are. This correlation allows for the creation of highly secure communication channels, where any tampering by a third party disrupts the entanglement and is immediately detectable. Another emerging concept is quantum secure authentication. Classical authentication relies on passwords or cryptographic signatures, which can be stolen or forged. Quantum authentication, however, leverages the principles of quantum superposition and entanglement to create authentication systems that cannot be copied or faked. These quantum-secured authentication methods could revolutionize online banking, digital identities, and access control systems. Despite its advantages, quantum cryptography is not without challenges. One major obstacle is the need for specialized hardware. QKD requires highly sensitive photon detectors, quantum light sources, and fiber optic or free space communication channels capable of preserving fragile quantum states. While some progress has been made in integrating QKD into existing infrastructure, large-scale deployment remains costly and technically demanding. Another challenge is the range limitation of current quantum communication systems. While fiber optic cables can transmit quantum signals over distances of hundreds of kilometers, losses due to scattering and absorption limit their effectiveness for long-distance communication. To address this, researchers are developing quantum repeaters, devices that extend the range of quantum communication by preserving and relaying quantum states without collapsing them. These repeaters are a crucial step toward realizing a global quantum network. Satellite-based quantum communication offers another potential solution. By transmitting quantum signals through space, where photon loss is lower than in fiber optic cables, researchers have demonstrated secure quantum key distribution over much longer distances. The Chinese satellite Michus, launched in 2016, successfully transmitted entangled photons between ground stations over 1,200 kilometers apart, marking a significant milestone in the field. The transition from classical to quantum-secured communication is already underway. Governments and corporations are investing heavily in quantum cryptography research, recognizing its potential for securing critical infrastructure. Financial institutions, defense agencies, and technology firms are exploring how QKD and other quantum cryptographic methods can be integrated into existing security frameworks to protect sensitive data from future quantum threats. One key application of quantum cryptography is in securing national and military communications. Traditional encryption methods may soon become vulnerable to quantum attacks, necessitating the adoption of quantum-secure channels for diplomatic, intelligence, and defense communications. Several governments have already initiated quantum communication networks to protect their most sensitive information. Beyond military and governmental applications, quantum cryptography could enhance personal privacy. Secure messaging services, online transactions, and personal data storage all rely on encryption to protect users. Implementing quantum-secure encryption could safeguard personal data against both current cyber threats and future quantum-enabled attacks. The financial sector is also poised to benefit from quantum cryptography. Banks, stock exchanges, and payment processors handle vast amounts of sensitive data that require secure transmission. By adopting quantum-secure encryption, financial institutions could prevent fraud, secure digital transactions, and protect against cyber attacks that exploit weaknesses in classical cryptographic systems. One of the biggest long-term goals in quantum cryptography is the development of a quantum internet, a global network of quantum-secured communication channels. Unlike the classical internet, which relies on conventional encryption techniques, a quantum internet would be inherently secure at the fundamental level. Quantum entanglement could enable instantaneous and tamper-proof communication between distant parties, eliminating many of the vulnerabilities associated with current digital networks. While full-scale quantum networks are still in the early stages of development, researchers are making steady progress. Quantum nodes, which serve as hubs for quantum communication, are being tested in experimental networks, and prototype quantum communication links have already been established in several countries. The realization of a large-scale quantum internet could redefine cybersecurity, enabling a future where digital communications are fundamentally protected by the laws of physics. Despite its potential, quantum cryptography does not eliminate all security risks. Physical attacks on quantum communication infrastructure, such as intercepting photon signals before they reach their intended recipient, remain a concern. Additionally, while QKD guarantees secure key exchange, it must be integrated with other security measures to ensure overall system security. The emergence of post-quantum cryptography presents another dimension to the evolving field of secure communication. While quantum cryptography focuses on using quantum mechanics to secure communication, post-quantum cryptography aims to develop classical encryption algorithms that can resist attacks from quantum computers. These algorithms, based on mathematical problems that remain difficult even for quantum processors, offer an alternative path to securing data against future threats. Looking ahead, the continued development of quantum cryptography will depend on advances in quantum hardware, communication protocols, and integration with existing networks. As research progresses, quantum-secure communication may become not only feasible but essential for protecting sensitive information in an increasingly digital world. Cryptography has always been a race between code makers and code breakers. Quantum cryptography represents a fundamental shift in this dynamic, introducing security mechanisms that are not just computationally difficult to break, but physically impossible under the laws of quantum mechanics. By leveraging the principles of quantum physics, the future of secure communication is being rewritten, offering a path toward encryption methods that are resistant to even the most advanced computational threats. Quantum cryptography is a fascinating field that promises to revolutionize secure communication. Another topic we should touch is quantum sensors. Precision measurement has always been at the heart of scientific and technological advancement. From mapping gravitational fields to detecting subtle changes in electromagnetic waves, the ability to measure with extreme accuracy shapes our understanding of the world. Quantum sensors, which leverage the principles of quantum mechanics, represent a significant leap forward in measurement technology. These devices exploit quantum superposition, entanglement, and tunneling to achieve levels of precision far beyond classical sensors, enabling breakthroughs in navigation, medical imaging, and fundamental physics research. Classical sensors rely on macroscopic properties such as voltage changes or mechanical displacement to detect variations in environmental conditions. Quantum sensors, however, operate at the atomic or subatomic level, where particles exhibit wave-like behavior and can exist in multiple states simultaneously. By maintaining quantum coherence, the ability of a quantum system to exist in a superposition of states, these sensors achieve extraordinary sensitivity. One of the most well-developed quantum sensing technologies is atomic interferometry. This technique exploits the wave nature of atoms to measure minute changes in acceleration and rotation. A common approach involves cooling atoms to near absolute zero, where their quantum properties become more pronounced. These atoms are then split into separate wave-like states, allowed to travel along different paths, and recombined. Any differences in their final states reveal information about the forces acting on them. This method has led to the development of ultra-precise accelerometers and gyroscopes, which are essential for navigation systems that do not rely on GPS. Gravitational sensing is another area where quantum technology is making significant contributions. Quantum gravimeters, which measure tiny fluctuations in gravitational fields, are being used to detect underground structures, monitor volcanic activity, and improve climate models. Unlike classical gravimeters, which rely on mechanical components that can drift over time, quantum gravimeters use freely falling atoms as reference points. Because these atoms experience gravitational acceleration in a pure and unperturbed manner, quantum gravimeters provide exceptionally stable and accurate measurements. Quantum magnetometers take advantage of quantum superposition to detect incredibly weak magnetic fields. Traditional magnetometers often struggle to measure fields at the scale required for applications such as brain imaging and geophysical exploration. Quantum magnetometers, particularly those based on nitrogen vacancy, NV centers in diamond, can detect minute magnetic variations with unprecedented sensitivity. These sensors are being explored for medical diagnostics, where they could enable non-invasive brain scans with greater detail than current MRI technology. One of the most promising applications of quantum sensors is in timekeeping. Atomic clocks, which use quantum transitions in atoms to measure time with extreme precision, are already the foundation of global positioning systems, GPS. Next-generation quantum clocks promise even greater accuracy, reducing time drift to levels where errors accumulate only by a fraction of a second over millions of years. These advancements could improve GPS reliability, facilitate deep space navigation, and enhance synchronization in global communications networks. Medical imaging stands to benefit significantly from quantum sensing. Traditional imaging techniques, such as MRI and PET scans, rely on strong magnetic fields and radiation, respectively, to generate images of internal body structures. Quantum sensors offer the potential for more precise imaging with lower energy input, reducing patient exposure while increasing diagnostic accuracy. For example, quantum-enhanced MRI could detect changes in biological tissue at the molecular level, enabling earlier detection of diseases such as cancer and neurodegenerative disorders. Quantum sensors are also being explored for applications in defense and national security. Advanced quantum radar systems, which use entangled photons to detect objects with greater resolution than classical radar, could improve stealth detection capabilities. These systems can potentially outperform traditional radar by being less susceptible to interference and providing better target discrimination. Similarly, quantum-enhanced sonar could revolutionize underwater navigation and submarine detection. The role of quantum sensors in fundamental physics is equally important. Experiments testing the limits of general relativity, searching for dark matter, and investigating quantum gravity rely on precise measurements that classical sensors cannot achieve. Quantum sensors have already contributed to some of the most sensitive tests of physical constants, refining our understanding of the universe's fundamental laws. Despite these advancements, significant challenges remain in the widespread deployment of quantum sensors. One of the primary hurdles is maintaining quantum coherence for long enough periods to complete accurate measurements. Quantum states are extremely fragile and can be disrupted by environmental noise, such as thermal fluctuations and electromagnetic interference. Researchers are developing error correction techniques and shielding methods to mitigate these issues and extend coherence times. Another challenge is scalability. While laboratory experiments have demonstrated the effectiveness of quantum sensors, integrating them into portable and commercially viable devices requires engineering breakthroughs. Advances in miniaturization, material science, and quantum control techniques are critical to bringing these sensors out of research labs and into real-world applications. Greater than. Quantum networking may offer solutions to some of these challenges. By linking quantum sensors together, researchers can create distributed sensing networks that improve precision and resilience. These networks could be used for global monitoring systems that detect subtle shifts in gravitational fields, electromagnetic waves, or atmospheric conditions with unparalleled accuracy. Governments and private industries are investing heavily in quantum sensing research. Space agencies are particularly interested in quantum sensors for space exploration, where precision navigation and gravity mapping are crucial. Earth observation satellites equipped with quantum sensors could track climate changes with extreme detail, improving weather forecasting and disaster response. In the transportation sector, quantum sensors are being explored for their potential to revolutionize navigation. Current GPS systems are susceptible to signal loss in tunnels, deep urban environments, and underwater. Quantum accelerometers and gyroscopes could provide autonomous navigation for submarines, aircraft, and spacecraft, reducing reliance on external signals and improving resilience against jamming or spoofing. Another emerging application is in the field of material science. Quantum sensors can probe atomic and molecular structures with unmatched precision, aiding in the development of new materials for energy storage, semiconductors, and nanotechnology. By mapping magnetic and electric fields at microscopic scales, these sensors allow scientists to understand material properties at a fundamental level. The impact of quantum sensing on cybersecurity should not be overlooked. Quantum random number generators, QRNGs, use quantum mechanics to produce truly random numbers, a critical component in encryption and secure communications. Unlike classical random number generators, which rely on algorithms that can be predicted or manipulated, QRNGs generate randomness based on quantum processes, making them impervious to hacking. Greater than. Looking ahead, the evolution of quantum sensors will likely transform multiple industries, from healthcare and defense to space exploration and computing. While the technology is still in development, its potential to surpass classical measurement limits is undeniable. Continued research into quantum coherence, miniaturization, and integration with existing technologies will be key to unlocking new capabilities. Ultimately, quantum sensors represent a profound shift in how measurements are conducted, offering levels of precision that were once thought impossible. Their applications extend far beyond laboratory research, holding the potential to redefine navigation, communication, medicine, and fundamental physics. Greater than. Let's explore another quantum phenomenon that has equally profound implications. Superconductivity. Zero resistance may sound like an impossibility in conventional electrical systems, yet in the strange world of quantum mechanics, it is not only possible, but forms the basis of superconductivity. This remarkable phenomenon occurs when certain materials, cooled to extremely low temperatures, allow electric current to flow without any loss of energy. Unlike ordinary conductors, where electrons scatter due to thermal vibrations and impurities, superconductors enable the unimpeded movement of electrical charges, revolutionizing fields ranging from power transmission to medical imaging and quantum computing. The discovery of superconductivity dates back to 1911, when Dutch physicist Heike Kamerlingh Onnes observed that mercury, when cooled below 4.2 Kelvin, suddenly lost all electrical resistance. This behavior was entirely unexpected, as classical physics suggested that resistance should decrease gradually as temperature lowers but never reach absolute zero. Further experiments confirmed that this phenomenon was not unique to mercury. Other elements and compounds also exhibited superconductivity under specific conditions. For decades, the exact mechanism behind superconductivity remained a mystery. Classical models of electricity, which describe the movement of free electrons through a lattice of atoms, could not explain why resistance would vanish entirely. The breakthrough came in 1957 with the Bardeen-Cooper-Schrieffer theory, which provided a quantum mechanical explanation for the phenomenon. According to this theory, superconductivity arises due to the formation of Cooper pairs of electrons that move through a lattice in a correlated manner, avoiding the scattering that typically causes resistance. In a normal conductor, electrons travel as individual particles and frequently collide with atoms in the material's structure. These collisions generate resistance, converting some electrical energy into heat. However, in a superconductor, electrons pair up due to interactions with the atomic lattice. This pairing is counterintuitive, because electrons, both negatively charged, should repel each other. However, the vibration of the atomic lattice, known as a phonon interaction, mediates an attractive force between electrons, leading them to form bound pairs. These Cooper pairs move in a collective, synchronized manner, creating a quantum state that allows them to flow without any disruption. One of the most striking properties of superconductors is the Meissner effect, discovered in 1933 by physicists Walther Meissner and Robert Ochsenfeld. This effect demonstrates that a superconductor not only allows current to flow without resistance, but also expels magnetic fields from its interior. When a material transitions into a superconducting state, it actively pushes out external magnetic fields, making it an ideal material for applications requiring strong, stable magnetic environments. This property is widely used in magnetic levitation technology, where superconductors enable frictionless motion, such as in maglev trains. While superconductivity was initially observed only at temperatures near absolute zero, the search for materials that exhibit this property at higher temperatures has been a major focus of research. The first breakthrough in high-temperature superconductivity came in 1986, when researchers Carl Miller and Johannes Bednortz discovered that certain ceramic materials, known as cuprates, could become superconducting at temperatures above 77 Kelvin, the boiling point of liquid nitrogen. This discovery was groundbreaking because liquid nitrogen is much easier and cheaper to produce than the liquid helium traditionally required for cooling superconductors. Since then, scientists have continued searching for materials that can superconduct at even higher temperatures. Some iron-based compounds have shown promise, and in 2020, a breakthrough was announced with the discovery of a room temperature superconductor, a hydrogen sulfide compound under extreme pressure. While practical implementation remains a challenge due to the requirement of high pressure, this discovery demonstrates that superconductivity at everyday conditions might one day be achievable. Superconductors have a wide range of applications, many of which are already transforming technology. One of the most well-known uses is in magnetic resonance imaging, MRI machines. These devices require extremely strong and stable magnetic fields, which superconducting magnets can provide without the energy losses associated with traditional electromagnets. This allows for high-resolution imaging of the human body without exposure to ionizing radiation. Another crucial application is in electrical power transmission. Traditional power lines suffer from energy losses due to resistance, leading to inefficiencies in long-distance electricity transport. Superconducting power cables, in contrast, can carry electricity with no energy loss, potentially revolutionizing power grids by making them far more efficient and reliable. Superconducting magnets are also vital in particle accelerators, such as the Large Hadron Collider, LHC. These accelerators rely on powerful magnetic fields to steer and focus beams of charged particles. By using superconducting magnets, scientists can achieve the necessary field strengths without excessive energy consumption or heat generation. Quantum computing is another field benefiting from superconductivity. Superconducting qubits, used in quantum computers developed by companies such as IBM and Google, rely on the ability of superconductors to maintain coherent quantum states for extended periods. These qubits exploit Josephson junctions, superconducting circuits that enable the precise control of quantum states, offering a scalable approach to quantum computation. Despite its advantages, superconductivity also presents challenges. Most superconducting materials still require extreme cooling, which makes widespread adoption costly and complex. Additionally, the materials used for high-temperature superconductors can be brittle and difficult to manufacture in practical shapes. Researchers are actively exploring ways to engineer new materials that maintain superconducting properties under more accessible conditions. The future of superconductivity holds exciting possibilities. If room-temperature superconductors can be made practical, they could revolutionize nearly every aspect of modern technology, from energy storage and transmission to medical devices and high-speed transportation. The elimination of electrical resistance could drastically improve efficiency, reducing energy consumption on a global scale. One area of interest is the potential application of superconductors in fusion energy. Fusion reactors require intense magnetic confinement to sustain the reactions necessary for energy production. Superconducting magnets could provide the necessary strength and stability, bringing practical fusion energy closer to reality. Another emerging area is in the development of superconducting electronics. Traditional semiconductor-based circuits generate heat due to resistance, limiting performance and efficiency. Superconducting circuits, on the other hand, could allow for faster and more energy-efficient computing devices, paving the way for entirely new generations of electronics. The role of superconductivity in space exploration is also being investigated. Superconducting materials could be used for advanced propulsion systems, radiation shielding, and power management in spacecraft. Their ability to maintain strong magnetic fields without energy loss could improve energy efficiency in deep space missions, where every watt of power is precious. Although superconductivity was initially discovered through curiosity-driven research, its applications have become indispensable in modern science and technology. From medical imaging to quantum computing and power grids, superconductors continue to push the boundaries of what is possible. The ongoing search for new materials, particularly those that function at ambient temperatures, could lead to breakthroughs that redefine the limits of efficiency and technological capability. Zero resistance may once have seemed like a theoretical curiosity, but today it is a key principle driving innovations across multiple industries. The quest to understand and harness superconductivity remains one of the most exciting frontiers in physics, with the potential to reshape the way energy is used, stored, and transmitted across the globe. The progress made in this field will determine how quickly superconductors transition from specialized scientific tools to mainstream technological solutions, unlocking a future where energy loss becomes a relic of the past. Greater than. Aside from superconductivity, there's another quantum effect that's equally fascinating: the quantum Hall effect. Imagine a thin layer of electrons moving in a two-dimensional plane, exposed to an extremely strong magnetic field. In ordinary conditions, electrical resistance behaves predictably, increasing with temperature and decreasing as materials become more conductive. However, in this unique environment, something remarkable happens. The electrical resistance becomes quantized, forming precise plateaus rather than changing smoothly. This phenomenon, known as the quantum Hall effect, reveals a fundamentally new state of matter, where electron behavior is dictated by quantum mechanics in ways that defy classical expectations. The quantum Hall effect was first observed in 1980 by Klaus von Klitzing, who discovered that when a strong magnetic field is applied perpendicular to a two-dimensional electron gas, such as those found in semiconductor interfaces, its Hall resistance, a measure of the voltage perpendicular to the applied current, exhibits discrete steps rather than continuous changes. These steps correspond to precise fractions of fundamental constants, specifically involving Planck's constant and the electron charge. This quantization remains astonishingly exact, independent of the material used or external disturbances, making it one of the most precise measurements in physics. To understand why this effect occurs, it helps to consider the motion of electrons in a strong magnetic field. Ordinarily, electrons in a conductor move randomly, occasionally scattering off impurities, which leads to electrical resistance. But in a two-dimensional system exposed to a high magnetic field, electrons become trapped in circular orbits called Landau levels. These quantized energy levels restrict their movement, leading to unusual electrical properties. At certain conditions, electrons collectively enter a highly ordered quantum state, forming what is known as a topological phase of matter. Greater than. Unlike conventional conductors where resistance depends on impurities and material properties, the resistance quantization in the quantum Hall effect is governed by fundamental constants. This makes it an essential tool for metrology, the science of precise measurement. In fact, the quantum Hall effect is used to define the international standard for electrical resistance, ensuring that measurements remain consistent worldwide. A particularly surprising aspect of this effect is the emergence of edge states, channels along the boundary of the material where electrons move without scattering. These edge states allow current to flow in a single direction, immune to imperfections or obstacles in the material. This property makes quantum Hall systems ideal for applications requiring highly stable electronic transport, such as quantum computing and low-power electronic devices. In 1982, a further breakthrough occurred when researchers observed the fractional quantum Hall effect, where the resistance steps appear at fractional rather than whole number values of fundamental constants. This discovery suggested that electrons in these systems behave in a fundamentally different way, acting not as individual particles, but as collective quantum states known as quasi-particles. Some of these quasi-particles exhibit fractional electric charge, a property that does not exist in standard physics. The emergence of fractional charges hints at deep connections between the quantum Hall effect and fundamental concepts such as quantum entanglement and topology. The role of topology in the quantum Hall effect has become a major focus of research. Unlike ordinary phase transitions, which involve changes in temperature or pressure, topological phase transitions involve changes in the global properties of a material's quantum wave function. These transitions are robust against disturbances, meaning that the quantum Hall effect remains stable even when impurities or external forces are introduced. This robustness makes quantum Hall systems highly promising for applications in fault-tolerant quantum computing, where preserving delicate quantum states is crucial. Greater than. Beyond fundamental physics, the quantum Hall effect has practical applications in next-generation electronic devices. The precise resistance quantization makes it invaluable for developing ultra-sensitive sensors and precision voltage standards. Additionally, the unique transport properties of quantum Hall materials have inspired research into new kinds of transistors and electronic circuits that could operate with minimal energy loss. The study of the quantum Hall effect has also paved the way for discovering other exotic quantum phases, such as topological insulators. These materials, like quantum Hall systems, support robust edge states that conduct electricity without dissipation. However, unlike quantum Hall systems, they do not require an external magnetic field to exhibit these properties. This discovery has fueled research into new materials with potential applications in spintronics, where electronic devices exploit electron spin rather than charge for information processing. Despite the remarkable insights gained from quantum Hall physics, many questions remain. One of the most intriguing areas of research involves non-abelian anyons, exotic quasi-particles predicted to exist in certain fractional quantum Hall states. Unlike ordinary particles, which behave as either bosons or fermions, anyons exhibit more complex behavior, changing their quantum state in a unique way when swapped. This property has profound implications for quantum computing, where anyons could enable topological quantum computers that are far more resistant to errors than current designs. Experimental advancements continue to push the boundaries of what is possible with quantum Hall systems. Scientists are exploring new materials, such as graphene, which exhibits an exceptionally strong quantum Hall effect, even at room temperature. The ability to harness quantum Hall properties without extreme cooling could open the door to practical applications in everyday technology. Greater than. In addition to laboratory research, quantum Hall physics has deep connections to other areas of theoretical physics. Concepts from quantum Hall theory have been applied to high-energy physics, condensed matter systems, and even black hole physics. The mathematical structures underlying the quantum Hall effect share similarities with those found in string theory, suggesting that these systems may provide insight into the fundamental nature of space-time. While the quantum Hall effect was once considered an obscure phenomenon confined to low-temperature physics, its impact has grown far beyond its initial discovery. It has provided a deeper understanding of quantum mechanics, revealed new states of matter, and inspired practical innovations that could shape the future of electronics and computing. Greater than. Let's move on to the next topic and discuss quantum dots. Nanites, microscopic machines imagined in science fiction, represent the dream of manipulating matter at the atomic scale. While fully autonomous nanorobots remain a distant goal, one technology is already bringing precision engineering to the nanoscale: quantum dots. These tiny semiconductor particles, only a few nanometers in size, exhibit remarkable quantum properties that make them essential in fields ranging from medicine and electronics to renewable energy. Their ability to emit tunable, highly efficient light has revolutionized display technology, and their role in biological imaging and quantum computing continues to expand. At their core, quantum dots are semiconductor nanocrystals small enough to exhibit quantum mechanical effects. Their defining feature is quantum confinement. When electrons are restricted within a space comparable to their wavelength, they behave differently than in bulk materials. In a typical semiconductor, electrons move freely, but in a quantum dot, their motion is constrained, leading to discrete energy levels similar to those seen in individual atoms. This confinement effect gives quantum dots their striking optical and electronic properties. One of the most remarkable aspects of quantum dots is their ability to emit specific wavelengths of light depending on their size. A larger quantum dot emits red light, while a smaller one emits blue, with intermediate sizes producing a full spectrum of colors. This tunability arises because the energy difference between electron states increases as the dot shrinks, altering the emitted photon's wavelength. Unlike traditional dyes or phosphors, quantum dots offer precise, stable color emissions, making them ideal for applications requiring fine-tuned optical properties. Greater than. One of the most commercially successful applications of quantum dots is in display technology. Quantum dot-enhanced displays, such as QLED televisions, use a backlight that passes through a layer of quantum dots, producing richer, more vibrant colors than traditional LED screens. The efficiency and purity of quantum dot-generated light improve color accuracy while reducing energy consumption, making them a key component in next-generation display technology. Beyond displays, quantum dots are revolutionizing medical imaging. Traditional fluorescent dyes used in biological labeling suffer from photobleaching, where their brightness fades over time. Quantum dots, in contrast, are far more stable, allowing for long-term imaging of cells and tissues. Their precise emission wavelengths enable multiplexing, where multiple quantum dot colors are used simultaneously to track different biological markers within a single sample. This capability has profound implications for cancer detection, drug delivery, and neurological research, where tracking specific molecules with high resolution is essential. In the field of renewable energy, quantum dots are opening new pathways for efficient solar power generation. Traditional silicon-based solar cells are limited in their ability to absorb sunlight, as they can only harness a specific range of the spectrum. Quantum dot solar cells, however, can be tuned to absorb different wavelengths more efficiently. Their ability to undergo multiple exciton generation, MEG, allows a single photon to excite multiple electrons, potentially increasing energy conversion efficiency beyond the limits of conventional materials. While still in the experimental phase, quantum dot solar technology holds promise for more cost-effective and efficient photovoltaics. Quantum computing is another area where quantum dots show great potential. Unlike classical bits, which are either 0 or 1, quantum bits, qubits, can exist in superpositions of both states. Quantum dots can act as qubits by trapping single electrons whose spin states encode quantum information. Their small size and ability to be precisely controlled with electric and magnetic fields make them promising candidates for scalable quantum computing architectures. Researchers are exploring ways to use quantum dots to build more stable, fault-tolerant qubits, which could eventually lead to practical quantum computers capable of solving problems far beyond the reach of classical systems. Greater than. Another emerging application is in quantum dot-based lasers. Unlike conventional semiconductor lasers, which require bulk materials, quantum dot lasers use nanoscale particles as gain media, reducing energy consumption while enhancing performance. These lasers have applications in telecommunications, optical computing, and medical diagnostics, where precise and efficient light sources are essential. Despite their promise, quantum dots also face challenges. One issue is material stability, as many early quantum dots contained toxic elements like cadmium, raising environmental and health concerns. Efforts are underway to develop cadmium-free quantum dots using alternative materials, such as indium phosphide, which offers similar optical properties without toxicity. Advances in synthesis techniques are also improving the uniformity and reliability of quantum dots, making them more suitable for large-scale commercial applications. Manufacturing quantum dots at an industrial scale presents another challenge. While laboratory methods allow precise control over quantum dot size and composition, scaling up production while maintaining uniformity and cost-effectiveness remains an ongoing area of research. Techniques such as chemical vapor deposition and colloidal synthesis are being refined to produce high-quality quantum dots for widespread use. Looking toward the future, quantum dots are expected to play a crucial role in emerging nanotechnologies. In medicine, they could enable targeted drug delivery systems where quantum dots are functionalized with molecules that bind to specific disease markers, allowing drugs to be delivered directly to affected cells. In electronics, quantum dot transistors may replace traditional silicon components, enabling faster, more energy-efficient circuits. Another exciting possibility is in quantum dot biosensors, which could detect minute changes in biological environments with unprecedented sensitivity. These sensors could be used in disease diagnostics, environmental monitoring, and food safety, offering real-time detection of contaminants or pathogens. The continued development of quantum dots also has implications for data storage. The ability of quantum dots to store and manipulate quantum information could lead to ultra-dense memory systems far beyond the capabilities of today's technology. Research is ongoing into how quantum dots could be integrated into next-generation computing architectures, potentially revolutionizing information processing and storage. As industries move toward greener technologies, quantum dots may contribute to sustainable innovations. Their role in energy-efficient lighting, solar power, and advanced sensors aligns with global efforts to reduce energy consumption and environmental impact. By improving material efficiency and reducing reliance on rare or toxic elements, quantum dot technology could support a shift toward more sustainable industrial processes. Nanotechnology continues to redefine what is possible at the atomic and molecular scales, and quantum dots stand at the forefront of this revolution. Their unique properties make them invaluable across multiple scientific and technological fields, from enhancing display technologies to advancing quantum computing and medical diagnostics. As research progresses, quantum dots will likely become even more integral to modern technology, enabling breakthroughs that were once considered purely theoretical. Quantum dots are a fascinating example of how quantum mechanics can be harnessed for practical applications. But there's another area where quantum principles are making waves: quantum biology. Quantum mechanics is often associated with subatomic particles, cutting-edge technology, and theoretical physics, but its influence may extend beyond laboratories and into the very fabric of life itself. The emerging field of quantum biology explores how quantum phenomena, such as superposition, tunneling, and entanglement, may play essential roles in biological processes. While classical physics governs much of the macroscopic world, quantum effects appear to be at work in fundamental aspects of life, from photosynthesis to enzyme reactions, and even the functioning of the human brain. One of the most well-studied examples of quantum mechanics in biology is photosynthesis. Plants, algae, and some bacteria rely on this process to convert sunlight into energy, using specialized proteins called photosystems. Traditional models suggested that light-absorbing molecules, known as chlorophyll, capture photons and transfer their energy through a network of molecules in a relatively random manner. However, experiments have shown that energy transfer in photosynthesis is far more efficient than classical physics would predict. This efficiency is believed to result from quantum coherence, where energy is not transferred as a single localized packet, but explores multiple paths simultaneously. In essence, the energy behaves like a wave, traveling through the photosynthetic system in parallel and instantly selecting the most efficient route. This quantum superposition enables plants and bacteria to capture and store sunlight with remarkable precision, far surpassing what classical energy transfer mechanisms would allow. Another biological process that appears to harness quantum mechanics is enzyme activity. Enzymes are molecular machines that accelerate chemical reactions, essential for life, often by factors of millions or even billions. One long-standing question in biochemistry is how enzymes achieve such extraordinary reaction rates. Recent studies suggest that quantum tunneling plays a crucial role. In classical chemistry, reactants must overcome an energy barrier to undergo transformation, requiring heat or other external energy sources. However, quantum tunneling allows particles, such as protons or electrons, to tunnel through these barriers instead of climbing over them. This means reactions can occur even at relatively low temperatures, which is critical for biological systems that operate under tightly controlled conditions. Evidence of tunneling has been found in enzymes such as alcohol dehydrogenase, which is involved in breaking down ethanol in the human liver. These discoveries suggest that quantum effects are fundamental to the speed and efficiency of biological chemistry. A particularly intriguing area of quantum biology involves magnetoreception, the ability of certain animals to sense Earth's magnetic field. Birds, sea turtles, and even some bacteria use this ability to navigate long distances with astonishing accuracy. The underlying mechanism for magnetoreception has puzzled scientists for years, as classical physics does not easily explain how biological systems detect weak magnetic fields. One leading hypothesis involves quantum entanglement, a phenomenon where two or more particles become interconnected, such that the state of one instantly influences the state of the other, no matter how far apart they are. In birds, researchers have identified a protein called cryptochrome, found in the retinas of migratory species. This protein contains pairs of electrons that, when exposed to light, become entangled. It is believed that changes in Earth's magnetic field influence these entangled electrons, providing birds with a quantum-based compass that helps them navigate across continents. Greater than. Quantum mechanics may also play a role in the sense of smell. The classical model of olfaction suggests that odor molecules fit into receptors in the nose, like keys fitting into locks. However, this explanation does not fully account for why molecules with similar shapes can have vastly different smells, while molecules with different shapes can sometimes smell nearly identical. An alternative theory proposes that quantum vibrations within the odor molecules influence their interaction with receptors. This idea, known as the vibrational theory of olfaction, suggests that electrons within the receptor proteins may undergo quantum tunneling, allowing the brain to detect distinct vibrational patterns associated with specific scents. One of the most speculative yet exciting areas of quantum biology is the potential role of quantum mechanics in consciousness and brain function. Neurons communicate through electrical signals and chemical reactions, but some researchers propose that quantum effects may contribute to cognitive processes. The orchestrated objective reduction, OR theory, developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests that quantum coherence occurs within microtubules, tiny structures inside neurons. According to this hypothesis, quantum processes could influence thought patterns, decision-making, and even the nature of consciousness itself. While OR remains controversial, there is growing interest in understanding whether quantum phenomena might play a role in neural processing. Some experiments suggest that warm, wet biological environments, once thought to be too noisy for delicate quantum effects, may actually support quantum coherence for longer than expected. If quantum mechanics is involved in brain function, it could provide insights into memory formation, learning, and the emergence of complex thought. Beyond these specific examples, quantum biology raises broader questions about evolution and the origin of life. Some researchers speculate that quantum effects could influence genetic mutations, providing a mechanism for adaptive evolution beyond traditional Darwinian processes. Quantum superposition might allow molecular structures to explore multiple configurations before settling on the most stable or advantageous one. This idea remains highly speculative, but if confirmed, it could redefine our understanding of how life develops at the molecular level. Greater than. Practical applications of quantum biology are beginning to emerge. Understanding quantum effects in photosynthesis could lead to the development of more efficient solar energy technologies, mimicking nature's near-perfect energy transfer. Insights from enzyme quantum tunneling could help design more effective drugs and catalysts for industrial processes. Quantum-based medical imaging techniques, inspired by biological systems, may provide new ways to diagnose and treat diseases at the molecular level. Despite its promise, quantum biology remains a young and evolving field. Much of the evidence is indirect, and many of the proposed mechanisms require further experimental validation. The challenge lies in detecting and measuring quantum effects in complex biological systems, which are far messier than the controlled environments of quantum physics laboratories. Advances in quantum computing, nanotechnology, and ultra-fast spectroscopy are providing new tools to probe these phenomena with greater precision. If quantum mechanics plays a fundamental role in biological processes, it challenges the traditional view that quantum effects are confined to isolated, low-temperature environments. Instead, it suggests that life itself has evolved to exploit quantum principles in ways that enhance survival, efficiency, and complexity. This realization could lead to new interdisciplinary collaborations, bringing together physicists, biologists, chemists, and engineers to explore the quantum foundations of life. Quantum biology is not just about uncovering hidden quantum effects in living organisms. It is about redefining the boundaries between physics and life sciences. As we delve deeper into the quantum realm, we may discover that the very essence of life is intertwined with the strange and counterintuitive principles that govern the subatomic world. By unraveling these connections, we not only expand our understanding of biology, but also gain new insights into the fundamental nature of reality itself.